Good morning. I'm France Cordova, Director of the National Science Foundation. I'd like to welcome our distinguished guests from the LIGO Scientific Collaboration, the Virgo Collaboration, and the Max Planck Institute. Members of the press, esteemed government officials, and scientists and representatives of ground and space-based observatories and supporting institutions from around the world. I'd like to specifically welcome Michael Kratsios, Deputy Assistant to the President and Deputy U.S. Chief Technology Officer, and Federico Farini, Director of the European Gravitational Observatory. Representing the National Science Board is Maria Zuber. We're delighted you all could join us for this event. In February 2016, we announced the first ever detection of gravitational waves, ripples in space-time, caused by the merger of two black holes in a binary system 1.3 billion light-years away. The detection, made by the National Science Foundation-supported Laser Interferometer Gravitational Wave Observatory, or LIGO, confirmed a major prediction of Albert Einstein's 1915 theory of general relativity and marked the beginning of a new field, gravitational wave astronomy. It also came decades after NSF and the National Science Board approved initial funding to Caltech and MIT to construct and operate LIGO. LIGO is an instrument so sensitive it can detect the smallest ripple in space-time, lasting only a fraction of a second. Gravitational waves can only be caused by the most spectacular cosmic events, as when one black hole collides with another. Following that first detection, scientists confirmed a few more detections of gravitational waves caused by colliding black holes, the most recent of which was in conjunction with Virgo. There is, of course, another event we were keen to detect. Today, we're thrilled to announce that scientists have detected gravitational waves coming from the collision of two neutron stars, the smallest and densest stars. This event occurred 130 million light-years from Earth in a galaxy far away. The LIGO detectors first picked up the signal. When Virgo did not see a signal of similar magnitude, it was clear the event was close to one of Virgo's blind spots. This enabled scientists to localize the potential origin of the signal more precisely, allowing ground and space-based telescopes, some 70 in all, to turn their attention there as well. What makes this discovery even more exciting is that scientists were also able to detect light, electromagnetic waves, from the collision. The very same cosmic event seen for the first time through multiple messengers, gravitational waves and electromagnetic waves. As an astrophysicist and someone whose passion for physics was first ignited by a television program on neutron stars, it's especially exciting for me to report on this rare event. Already it is transforming our understanding of the universe, with a fresh narrative of the physics of stars in their death throes. The scientists who conceived of building LIGO and were primary drivers, Kip Thorne and Barry Barish of Caltech and Rainer Weiss of MIT, are receiving the 2017 Nobel Prize in Physics. Their vision and perseverance and NSF support made this discovery possible. This is what NSF does. We invest in high-risk, high-reward research that produces the discoveries that transform our world and advance the frontiers of knowledge. The benefits of these discoveries are not confined to the scientific community, but extend throughout the world, as discoveries from basic research coupled with novel engineering often do. Today's announcement should excite the scientists and non-scientists. It's a measure of what is possible when we have the courage to push beyond the limits of our knowledge and pursue answers to big questions. At this point, let me turn the program over to Dr. David Reitze. When we first announced the first gravitational wave discovery a year ago, David captured the excitement of the moment when he declared, "We did it." Well, Dave, we did it again.
Thank you, Dr. Cordova. Good morning, ladies and gentlemen. We have, for the first time, seen both gravitational waves and light from the collision of two dense dead stars called neutron stars. However, to do it this time, we joined forces with thousands of astronomers and many, many observatories. So we did it again, but this time we all did it. Let me start by telling you what we saw. The LIGO Virgo network discovered two neutron stars colliding together. So LIGO is the LIGO Hanford and Livingston Observatory here in the United States. Virgo just started operating in August of this year. And we saw a signal at 8:41 a.m. Eastern Time on August 17th. The signal was much different from the black holes that we had detected before. It was much longer. And we analyzed this signal. And what we found was that it was a neutron star, approximately 1.6 solar masses, colliding with a second neutron star, approximately 1.1 solar masses, about 130 million years ago, 30 million light years away. So this graphic that you're seeing here is just the brief second where they collided. Now, this is a source that we always thought we would saw. Neutron star systems, binary neutron star systems have been predicted for decades, and we knew that we would see them. For me, what makes this event so amazing is what came next. The emission of light across the entire electromagnetic spectrum, revealed to us by a campaign involving 70 observatories, including 7 space-based observatories and every continent on the planet. So if you look at the graphic carefully that I'm showing, you'll even see there's a dot in Antarctica. So this is quite dramatic. This is an amazing, amazing discovery. And it was made possible by the fact that LIGO and Virgo, operating together, can identify the place in the sky where this event came from. It came from the southern hemisphere. It came from the Hydra constellation. So let me tell you a little bit about neutron stars. Neutron stars are very different from black holes. Now, they're produced from supernova, the explosion of massive stars. They're approximately 1 to 2 times the mass of the star. However, they're made up of pure neutrons. And the density of the neutrons in the neutron star is much, much greater than atomic nuclei, actually about a factor of 3 times greater. So consequently, they're very compact. Neutron stars are about 20 to 25 kilometers in diameter, and you can see in this graphic that I'm showing you the Bay Area and San Francisco. That peninsula is San Francisco. So what you're seeing there, to get a sense of this, is 1.5, 1.6 solar masses packed into a very, very compact region. So, all right, what does this really tell us? Well, astronomers have thought for a long time that the collisions of these neutron stars produce heavy elements, and there's been hints of that in other astronomical observations. But this result provides definitive evidence for the first time that elements such as platinum, gold, uranium are actually produced in these collisions. So I'm going to take out this is my great-grandfather's gold watch. It's about 100 years old. The gold in this watch was very likely produced in the collision of 2 neutron stars approximately billions of years ago. We don't know exactly when. So this is really an amazing discovery. You're going to hear today from the physicists and astronomers who participated in this remarkable discovery. In fact, the scientific story is so rich that it takes 2 panels to tell it. So you're going to hear from 2 different panels today. For me, the story is actually, the big story is the fact that we're now using this new tool called gravitational wave astronomy, and we're combining it with traditional and very powerful electromagnetic astronomy to study the most powerful events and violent events in the universe. All right, so the analogy I'll give you is this is the first time the cosmos has provided for us what I would call a talking movie. We've moved from the era of silent movies to talking movies. In this case, the audio soundtrack comes from the chirp of the neutron stars as they are inspiraling, as they're orbiting together and colliding. And the video is basically the light that we see after the collision. Right, so before I step down, I actually want to also acknowledge that this kind of science does not happen without sustained support from agencies, and in our case, it's the National Science Foundation, which has steadfastly funded us for over 3 decades. And this is, again, another example of what I would call high-risk, high-reward science, where NSF swang for the fences scientifically back in the 80s, and we've yet again hit a home run. So I'm now going to call my friend and colleague David Shoemaker to the podium, and he's going to tell you a little bit about gravitational waves and how we detect them.
Thank you, Dave. I'm an instrument builder, and so I want to tell you a little bit about how these instruments actually can function. But first, let me say a bit about gravitational waves. Let's imagine you have a wave that's coming at you. The effect is to squeeze space along one axis and stretch it on the other, and then squeeze and pull in this direction. But space is incredibly stiff, and the result is that this event, some 130 million light years away, only made the smallest change you could imagine. If you had, for instance, a yardstick and the gravitational wave were to pass next to it, it would change length by less than a billionth of a trillionth of an inch. On the other hand, if you say, what's the change in distance to Alpha Centauri, some 4 light years away? It changed by the thickness of a human hair. So that's how small the effect is, and that's our measurement challenge. So one of the things, though, I just said is that you get a bigger effect if you go further away. The gravitational wave is a strain in space. It's like stretching a rubber band. And when you stretch a rubber band, let me get to the right film here. Good, there we are. When you make a longer baseline measurement, you have a signal which is larger. And that's why LIGO and Virgo have arms which are miles long to boost up the signal to the point where it can actually be measured. But you still need some of the most sensitive devices that have ever been made to have a sensitivity that suffices to get a measurable signal. You also need, critically, hundreds and hundreds of people who can design and build and install and run these instruments, and then thousands of people around the world in the LIGO and Virgo collaborations who then can analyze the data and get something useful out of it. So now we're going to look at a simulation of an interferometer. We use interferometry. We compare the peaks and troughs in light waves that travel down the 2 arms and then back together again. Now, between the peaks of the light we use is about a billionth of an inch. But in fact, we can split that down by another factor of a billion by using very powerful lasers. Really, it's the quantum effects of light that limit how well we can do. And with that, we can actually get to a signal that is measurable when the gravitational wave passes and shifts those wavefronts by a tiny amount. So software is constantly scanning the data that comes out of this interferometer and matching against hundreds of thousands of templates. We're looking for a match between what we see in the wiggles in the data and these different waveforms. The first time we saw this signal, it was in the Hanford detector up in Washington. That was where the signal was the cleanest and easiest to see. About that same time, though, we saw a gamma ray alert. Julie McHenry will tell you a bit more about this in just a minute. And that is a thing that made us realize that we were at a watershed moment for multi-messenger astronomy. We quickly put together a sky map that was based on the signals that we saw in Hanford, Livingston, and Virgo to form an idea of where this was in the sky and to give the astronomers a sense of where to look. That morning, I was talking with Laura Caudinanti about some rather boring bureaucratic matters that we're spokesperson and deputy spokesperson of the collaboration, and we were trying to figure out how we could get the collaboration to change its way of thinking for the post-detection era when suddenly the phone alerts went off, and we immediately jumped over to the voice channel where all of the experts had gathered to try and understand where we were, and we shared in the joy and excitement of that moment. Now, while earlier detections of the black holes that we'd made, you can see it in the upper left-hand corner of this graphic, of this simulation, only lasted for us a couple of seconds or much less. This neutron star in spiral lasted for over a minute. And that's because these are lighter masses than the ones we've seen before. They're only about the mass of the sun, or 2 times the mass of the sun. And as a consequence, their frequencies are shifted up into a region which matches better the most optimal place in our instrument response function. And the result is that we can see the system for some 1,500 complete cycles of these 2 objects around each other. And it gives us a chance to get a very precise measure of the parameters of the system. But you have to imagine this. We've got these 2 objects, each one about the mass of the sun, but collapsed down to objects that are only 10 or 15 miles across, spinning around at close to the speed of light. That's a simulation, but that's what it sounds like also in the data. Spinning around at close to the speed of light so that they are eventually mixed together to make a single final object. It's an absolutely astonishing idea. We'll hear more about the fireworks that took place after the 2 fell together in terms of all the electromagnetic follow-up. Well, the resulting object and its electromagnetic radiation really is a treasure trove of information and is going to lead, I think, for months or perhaps even years of study to understand better exactly what happened with these 2 objects. We don't actually know what happened to the objects at the end. We don't know whether it's a black hole or a neutron star, or perhaps something else. Some of the panelists later on will give some of the ideas of the evidence that they have for one choice or the other. Maybe some continued observation will lead to a really complete and final answer. Well, with that, I'd like to turn the podium over to Jo van den Brand. He's my opposite number in the Virgo collaboration, and he'll talk a bit about how we were able to point the astronomers to the right place in the sky. Jo.
Thank you, David. So the brand new European Virgo detector joined LIGO in the 2nd observation run in the month of August. We joined for 3.5 weeks, and it were the most spectacular weeks. It went beyond all our most optimistic expectations. So now we have a 3 detector network, and this allows us to localize the sources much better. So the gravitational wave first arrived in the Virgo detector. And then 22 milliseconds later, it was seen in the detector, LIGO's detector in Louisiana, and another 3 milliseconds later, it arrived in the Hanford detector in the state of Washington. So this allowed LIGO and Virgo to pinpoint the source of the signals to about 30 square degrees in the Hydra constellation. And this is by far the most precise sky localization of all gravitational wave events so far. So to get an impression about that, you see here the first binary black hole events detected by the 2 LIGO detectors only. And you see that the average sky localization, so projected on the sphere of the Earth, is about 1,000 square degrees. So now if you include Virgo, you get a global 3 detector network, and the sky localization dramatically improves. So this event was relatively close by. The SNR was the highest of all gravitational waves detected so far. So you might be surprised, why is the signal so low in Virgo? So now every detector has an antenna pattern, and that is shown on the slide there. And there are places in the sky, actually 4 spots indicated in dark, where the detectors are not very sensitive. Now you see also in the star where the source of gravitational waves was, and it was near a bright spot, near the most sensitive region of LIGO. On the other hand, in Virgo, the signal was hiding near a blind spot, and that explains why the signal was low. Still, the information in Virgo was sufficient to do the localization, and this allowed the follow-up studies to proceed. So with LIGO and Virgo, we could look at the source and identify these 2 neutron stars. And this was followed by a flash of high-energy radiation seen first by Fermi, and later also by Integral. And you see the common sky position indicated by the electromagnetic signals. So then you can look at the LIGO information. This is this circle on the sky. And combining that with Virgo, you see now that the gravitational waves point at the same sky location as you independently find from the gamma ray burst observatories. Now, if you look into that, then this region contains about billions of stars, about 50 galaxies, and it took a little bit over 10 hours for the astronomers to find the optical counterpart and the galaxy. So all this, I think, is an unprecedented demonstration of a global effort involving thousands of research universities and institutes and scientists, and looking all at the same single astrophysical phenomenon. With gravitational waves from LIGO and Virgo, we could see the source in fantastic detail, and then follow up by this flash of high energy radiation detected by the satellites. And then subsequently, the source was studied in more detail by thousands of astronomers. The importance, the role of NSF was already pointed out, but I also would like to add that the realization of Virgo was possible because of the continued funding by both CNRS in France and by INFN in Italy, and later in the last decade followed by the Netherlands, by Hungary, Poland and Spain. So we did a lot of science, from fundamental physics to astronomy to astrophysics. We actually started right now on cosmology and nuclear physics. And I think this is a demonstration of what mankind can achieve if we put our minds to it and if we collaborate. So I think it's the start of a beautiful new field in science. And with that, I would like to hand over to Judy, who will talk about how Fermi saw the high energy radiation. Please.
Yeah. Gamma rays, the highest energy form of light, kicked off the light show. The gamma ray burst monitor on the Fermi Gamma Ray Space Telescope views the entire sky that is not blocked by the Earth. Around twice a day, we detect flashes of gamma rays. Flashes of gamma rays from thunderstorms, gamma rays from flares from our sun, outbursts of gamma rays from exotic stars in our galaxy. And important for the discussion here, a few hundred times a year, we see a brief flash of gamma rays from a gamma ray burst, a huge explosion in galaxies far away. August 17th started off as a perfectly normal morning for Fermi. We had breakfast. A gamma ray burst was detected, which by itself is not particularly surprising because we see quite a few of them. We saw a brief flash of gamma rays lasting just under 2 seconds. Half an hour later, we got an email from a colleague at Marshall Space Flight Center who works on both Fermi and LIGO saying, "Wake up!" in an email, which didn't actually wake us up, but okay. This burst has an interesting friend. And a few minutes later, we got a formal report from the LIGO and Virgo teams saying that they had detected a gravitational wave signal consistent with merging neutron stars just 1.7 seconds before the gamma ray burst detected by Fermi. And here I show the gravitational wave strain plot seen by LIGO. Half an hour later, we received another report from scientists working on Integral, a gamma ray observatory operated by the European Space Agency, who said that they had also seen the gamma ray burst. And with this started the most exciting morning of the 9-year Fermi mission. And the reason that this was so exciting is that there had been a long-held prediction that gamma ray bursts, these enormous explosions, that some of them, the ones that are short in duration, were powered by neutron star mergers. So within the first few minutes of getting this email, we realized that we had actually confirmed this prediction. So what do we think is going on? You've got 2 neutron stars that are spiraling around each other, spiraling closer and closer together as they lose energy by radiating gravitational waves. When they finally merge, they produce a huge energy release that powers jets that expand out into the material between the stars. We believe the gamma rays are produced in these jets. So this is great. We've solved a long-standing problem, but we're intrigued. In the Fermi detector, this looked like a perfectly normal gamma ray burst, just like any other short duration gamma ray burst that we see. But we knew from the gravitational waves that this burst was located more than 10 times closer than any other short burst with a measured distance. So it should have appeared very bright. So what's going on? One possibility is that we're not viewing this gamma ray burst down the barrel of the jet in the way that we usually do, but perhaps we're viewing it at an angle. Just as if you have a flashlight that dazzles you when you look straight at it, but if you're looking at an angle, it appears dimmer. With these observations, we're not just learning what happens when neutron stars collide. We're also learning something fundamental about the nature of the universe. The gravitational waves and the gamma rays traveled across the universe together for 130 million years and arrived within 2 seconds of one another. That's telling us that the gamma rays and the gravitational waves are both moving at the same speed, at the speed of light, as predicted by Einstein. So yet again, Einstein passes another test. So the story didn't stop there. The observations continued, revealing new and exciting features that the next speaker, Marika Brancesi, will tell you about. Thank you.
So Julie told you what Fermi saw in the sky, and I want to tell you what is the following story. So around 9 a.m. Eastern Time, about 90 group of astronomers around the world were alerted about the presence of the discovery of a gravitational wave signal coming from the coalescence of 2 neutron stars, 2 seconds before the gamma ray burst. A key moment happened about 4 hours later, when we sent the sky localization of the gravitational wave signal obtained with the LIGO and Virgo observatory. The sky localization was pretty good, and this source was close with respect to the other detected before. So a small universe and a nearby universe to be observed, a part of the universe where we know the galaxy. And at this point, all the observatory around the world start to look at the sky. And in particular, this source was located in the southern hemisphere, an ideal place for the Chilean telescope to look at that. And the Chilean telescope started to look at our sky localization at the twilight, and the first light escape has appeared as a very new bright object in one of these galaxies, NGC 4993, that is at the same distance of the gravitational wave source. We observed this object in all its colors, starting from gamma ray, then the blue ultraviolet light that fade rapidly and evolve in a red infrared object over a week. And then we discover also an X-ray emission and the radio emission after 9 days and after 16 days. This amazing discovery comes from a collaborative effort of different communities and 70 observatories that, including 100 instruments, they look at the same position of the sky for weeks. Each night observation brought a new piece to the puzzle to understand the neutron star and the engine that power light and sound. This is the start of the multi-messenger astronomy that allows us to hear the sound of the gravitational wave and at the same time to see the colors from the light. And the multi-messenger astronomy use different wave and different particles to observe the sky, also neutrinos. This time we didn't detect neutrinos, but we hope to add this messenger in our future observation. So the light in some band are expected also after years after the merger. But all is decided in a very small amount of time. When the two neutron stars dance around each other, became very, very close, about tenths millisecond before the merger, they start to feel tidal effect, tidal forces. And up to a few seconds after the merger, a matter is violently ejected in the interstellar medium. And this matter is the perfect site where heavy element can form. And the radioactive decay of this element powered the light that we saw in the blue, red, and near infrared. And this was predicted by the theories before. And we obtain amazing data, and some of them are, for example, from the telescope, the ESO VLTX shooter, Gemini, and the Hubble Space Telescope. And now I show you this data taken by the VLTX shooter. Here you can see a brightness decrease very, very rapid from the first to the second day. And from the third day, you can see in the spectra some broad feature that evolve. And these broad feature are the result of broad line blended together coming from this heavy element. So when the light escapes the matter, the universe is enriched by heavy element, and heavy element including also gold and platinum. So this, for the first time, we have observation that a large amount of these elements heavier than iron, form in this type of merger. And we learn a lot about neutron star and their life in the galaxy, and Vicky Calogera will talk about this in the next talk.
Thank you, Marika. Ooh, fast. There we are. So what I would like to do in the next few minutes is tell you a little bit about the history of two neutron stars in a pair, and also the history of this particular discovery. So this is the first time that we hear the death spiral of two neutron stars, and we also see the fireworks that came from the final merger. But for decades, thanks to observations, astronomy observations in the radio wavelengths of light, we have known that pairs of neutron stars exist. It turns out that neutron stars are not just highly compact, as Dave Wrightsey already told us, but they are also acting as cosmic radio lighthouses. So they emit radio jets, and when those radio jets, as the neutron stars are spinning around their own axis, when those jets are crossing our radio telescopes here on the Earth, then we see radio pulses. So back in the late 60s, Jocelyn Bell Burnell and Tony Hewish discovered neutron stars as radio pulsating stars, pulsars, in our own galaxy. And we now know that many neutron stars actually appear as pulsars. And just a few years later, in 1974, Russell Hulse and Joe Taylor discovered the first ever actual pair of two neutron stars. One of them was actually observed as a pulsar. The other might be a pulsar, but for sure we knew it was a neutron star. And they were found in an orbit that radio observations allowed us to tell that the orbit was not stable, but the orbit was a spiral-in orbit. And the spiral-in was happening as fast as Einstein predicted it should happen, based on the emission of radiation of gravitational waves. It was the observation of this system that was discovered by Hulse and Taylor that actually provided the very first firm evidence that gravitational waves existed in nature. And it was this system that made gravitational wave astronomy a dream worth pursuing. In the Hulse-Taylor pulsar, we know that the two neutron stars are actually very far away from one another. They are over 1 million miles apart, 5 times the distance between the Earth and the Moon. And they will not merge for another 300 million years. But this discovery we are announcing today, when the two neutron stars entered and we could hear them with LIGO and Virgo, they were just 200 miles apart. And of course, more than about 100 seconds later, they merged. However, before their final 100 seconds, they had a long life together as a pair. And it turns out that before the second neutron star was formed in the system, it was the system, the progenitor of that pair of neutron stars, had a long, quiet life in its home galaxy. So it was going around its business, orbiting its own galaxy in a quiet orbit. The green orbit, it was green, the orbit in the galaxy, until the second neutron star was formed, and the system was kicked in the galaxy in the last phase of its life. And it was kicked in an orbit that allowed it to visit all kinds of neighborhoods in the galaxy. It went on a vacation at the last part of its life, touring all around, having new experiences all around the galaxy before the two neutron stars found their death together as a pair. And we can tell all of this by having the information from gravitational waves and electromagnetic waves. Now, what you see in the movie is that there's lots of little dots there. We haven't discovered lots of little mergers. We have seen one merger. But when we do our computer simulations, we cannot isolate a single orbit in the galaxy. We have a collection of orbits that are likely the history of this system in terms of its motion in the galaxy. So overall, I would like to highlight, as other speakers have done, that what's amazing with this discovery is that theoretically, all of this that was observed on August 17th was actually predicted. So over a century ago, Einstein predicted that two orbiting objects will emit gravitational waves as they spiral in. And astrophysicists predicted that as the two compact objects, especially neutron stars, collide, they should emit gamma rays in jets. And a cascade of light across the whole electromagnetic spectrum was predicted, and the production of heavy elements that might include gold and platinum should be produced. So it's amazing to think that in one day, in a few hours and the weeks that followed, all these predictions were confirmed. So we solved a lot of mysteries, but at the same time, we also opened up a few questions. As Julie said, not everything fits perfectly in the puzzle. So we're opening up a new set of questions. We're hoping that future observations that for sure are going to happen, both with LIGO Virgo, but also with our electromagnetic partners, are going to answer a lot of those questions. So the future for multi-messenger astronomy is definitely bright, and I might say golden bright. Thank you.
Right. Thank you to all our panelists, and we're now open for questions. Yes.
Seth Borenstein, the Associated Press. As Vicky just said, this was most of the things from the heavy elements, the art process, to the Hubble constant and gamma rays were all theorized already and confirmed. What was the most surprising things you found, the new puzzles? What didn't fit that you now have to go and find, as opposed to what you confirmed?
So one thing was mentioned by Julie. Maybe she will elaborate. I mean, the faintness of the gamma rays, even though the source we know from the gravitational waves is so close by, is definitely a mystery. And I would say the delay probably in the X-rays might be a connected mystery, and you're going to hear a lot more about this from the second panel. And others may have something more to add.
Right. Another question, please? Here.
Yeah, so given the light activity
Could you identify yourself, please?
Oh, Yun Yu from Inside Science. So given the light activity that's predicted by the model during a neutron star merger, is there anything to gain, perhaps to implement some kind of automated system so that all the telescopes can point before even humans are aware of the event?
Yeah, that's Marika. Why don't you take that?
Yes, it's very important because, okay, this object was close and the region of the sky was small, and we expect more distant sources. We expect also to have a bit larger region of the sky to observe. So it's extremely important to have a robotic telescope that look at the sky continuously, and also automatic system to analyze the data and to remove all the contaminants, because we have transient objects in the sky, objects that appear and disappear, and some of them are very similar to the counterpart of a gravitational wave signal. And so this is an extremely important part of this discovery.
Right, question here.
Hi, Sarah Kaplan from the Washington Post. You all have talked a lot about the significance of multi-messenger astronomy and how that's a big revolution. Can you talk about are there specific astrophysics questions that we're going to be able to answer now that we have these two messengers, particularly ones that readers who are maybe not physicists will be able to understand?
Let me try and take a crack at that. So another source that we would love to see, and that we would not only see in light and gravitational waves, but also in neutrinos, is a supernova explosion. All right. The problem with the supernova explosion is that we have to get really lucky, because they're very weak emitters. We can't see them outside our galaxy. They produce, tiny, tiny fractions of mass converted into gravitational wave energy. So they happen about once every 50 years. But certainly in the future, when we're running, we're going to be looking for that. And there are going to be more gravitational wave detectors that are coming online in the next 2 to 5 years, that when some of the detectors are down, some of them will still be running. So we'll hopefully still be able to capture them.
Can I add something to that, David? The other thing, if we collect more of these sources, these binary neutron stars, as we did so far, then we also can start getting into cosmology. So for example, right now, already with this first event, we get sensitivity to the Hubble constant. And given our analysis, if we build up more of these events, we get more and more a handle on cosmological questions.
Right. Any other questions? All right, then we'll take a short break. I'm sorry, is there?
We have a number of questions from the...
Oh, okay, Lisa? Yeah.
Yes, thank you.
So this is questions from the webcast.
From the webcast, that's right. Rashmi Shivni asks, scientists saw signatures of recently synthesized heavy metals like gold and platinum, which basically solve the long mystery of where half of all the elements heavier than iron are produced. So, can we predict the frequency of these neutron star mergers events based on the proportion of heavy elements we see in the universe?
So actually, we can indeed attempt to do that. And one of the publications that is being released from the LIGO Virgo collaboration is attempting to do this kind of calculation. And I am sure I haven't seen all the publications that are being released today from our electromagnetic partners. So other colleagues might have attempted to answer that question. But I will say the following, that the question of how often these mergers happen is much better answered by the observation itself in gravitational waves. So not from the calculation of what's the quantity of these heavy elements we have. Because we have a high uncertainty for how much gold or platinum we're forming in each event. So the uncertainty associated with that is quite high. Instead, we know how long LIGO and Virgo have operated so far, and we know that we have detected one event, and we can calculate a rather tight constraint relatively to previous constraints. We have now a tighter constraint on how often these mergers happen. And just to give you an idea, these are very rare events. So with this one event, we can tell that in a galaxy like the Milky Way, our own galaxy, maybe they're happening somewhere between, very rough numbers, between 30 and 500 events in our galaxy per million years. Okay, so don't hold your breath about a merger like this in our galaxy. The only way we could see one in a couple of years of LIGO operations, for example, is because LIGO and Virgo are listening to millions of galaxies, tens of millions of galaxies. And this is why we can get one in a couple of years, roughly speaking.
Okay, but it's a very good question, and the next panel may also shed some light on that. And I think it's going to keep theorists very busy working on that kind of question.
We have some more questions. With the merger of the two neutron stars and the kilonova, is the end state object a neutron star as well? And this question comes from Greg Redfern from WTOP Radio.
Okay, and I think David Shoemaker made some comments about this.
Say that we actually don't have any firm knowledge of what the final state is. There are some signs, you'll hear about this again in the next panel, some observations that have been made with the observation of X-rays that suggest that it should be a black hole. But in terms of its mass and all of the gravitational wave data, it could be either one of the heaviest neutron stars that's ever been seen or one of the very lightest black holes that's ever been seen. What we do hope, though, is that with a bit more observation, a bit more data, a bit more evolution of the source, that we'll have a more firm answer to that question.
Great. Another question from Camille Carsteel from Sky and Telescope. Are you able to say anything about the neutron star's equation of state, their radii?
Marika, you want to try that, or you want to give it to Vicky?
I think that the next panel will talk about this, and our gravitational wave data allow us to put some constraint on the equation of state and disfavor some type of equation of state, the stiffer one. And Laura Cadonati will talk about this in the bigger one in the next panel.
Here's another question from a freelancer, Meg Evans-Smith, who asks, what happens to the heavy elements that were produced during this collision?
Okay. Who wants to?
Okay, I can say something.
Yeah, go ahead.
But I think that the second panel is the perfect one to answer all these questions. Okay. So this ejecta is spread in the universe. So from these elements that are spread in the universe, then you have also formation of other stars and propagate. And so what we have now, for example, in the Earth, is something that probably arrived from a merger of neutron star, and this dissemination of elements in the interstellar medium.
One more question. This is a question from Robert Kushner from Gordon and Betty Moore Foundation. What limits the sensitivity of LIGO today? What are you doing to improve it? This could raise the state of discovery from 1 a year to 1 a month. Then you'd really be an observatory.
Yes, yes. All right.
And we'd be tired.
Go for it.
What a great question.
We currently are not observing because, well, we ended our observing run on August 25th, and we're taking a year off now from observing to do just that, to improve the sensitivity of the instruments. All of the instruments, both the LIGO instruments and the Virgo instrument, were working at a fraction of the sensitivity for which they were designed. But it takes years of time to tune these instruments up to their full sensitivity. We expect to be able to increase the overall network sensitivity in this coming year of activity by about a factor of 2. That increases the distance to which we can see by a factor of 2, and thus the volume of space that's included by a factor of 8. The obvious answer to the question of what kinds of rates we could expect, something like 8 times as frequent signals as we've currently been seeing. So we might be going from 1 every couple of months to 1 every couple of weeks or 1 a week. The thing for which we have the best estimate of rates now, the question was posed before about binary neutron stars, is binary black holes. And so that's the kind of source that we're most sure that we'll be seeing at this greater rate. But I think all kinds of signals will come in more frequently. And ones that are nearby will come in with a signal-to-noise ratio that's a factor of 2 better, so that we can examine the waveform with even more precision and extract more information. So once again, the future is bright. We are going to have to talk a lot in our collaborations about how to deal with so many new events and so many new papers to write. It's a wonderful dilemma to have.
And also, we're looking forward to our colleagues in other countries developing their gravitational wave detectors, and then joining in the collaboration and increasing the positions of these sources and the detections of them. So, in addition to improving our current sensitivity of the detectors, we expect many more to join us in several years' time. So that concludes our questions. Thank you very much. And we will be starting the next panel at 11:15. Is that right? Is there any change in that? 11:15? Okay. All right. Any more questions before we take a break?
Hi, I'm Anna Khan from the LA Times. Just a quick one. If these events are responsible for about half of the elements heavier than iron, what's responsible for the other half?
That's a good question. Marika?
So, many elements are formed in supernovae, so or when a star died. So the majority is supernovae. And supernovae were expected also to emit these, to form these heavy elements. It's more difficult, so the supernovae are more frequent with respect to the neutron star merger, but the amount of heavy element form are larger in this type of in the merger of two neutron stars.
Okay. All right. Well, thank you very much. And we have a really exciting panel of 10 observers from all over the world who caught this at various wavelengths coming up at 11:15, and they will fill in lots of the color and detail on this amazing observation. So thank you, and we'll conclude with the break right now.
Candles in the middle.
We're live? Oh, we're live. Okay, hello, and welcome to the LIGO Virgo YouTube Q&A. Yep. Okay, hi. We are streaming live from the University of Florida Physics Department. I'm Anna. I'm going to be hosting the session. I'm a Marie Curie Fellow here, working in analysis. And also beside me we have Ryan and Peter, and these are the instrumentation guys. They look at actually getting the detectors working. Space, so more Lisa, and then Ryan for LIGO. And we've got Kendall above me coming in from Monash University in Australia. She did her PhD here in UF on multi-messenger. Kendall, hi. Thank you for joining us. Okay, so we have our first questions coming through. First question is from Philippe Nichansky, and I apologize if I ever pronounced anybody's name wrong. Do you think discovery is more important than the one from last year, since it basically offers independent confirmation for LIGO and Virgo in the EM spectrum? Okay, guys, what are we thinking about this? So for me personally, it is well, I mean, I think the first one is always going to be the most exciting, because I spent my life looking at gravitational waves, well, at least the last 11, 12 years, and actually find that they really do exist, and having dedicated 12 years to nonsense was a very good feeling. How did you guys feel?
Yeah, obviously the first one was very exciting. Also because it was such a violent explosion. You know, it was seeing these three solar masses of mass being converted into pure energy. It's one of the most violent explosions we've ever seen in the universe. But I think today's announcement, where we're seeing a signal that we can see evolve inside the measurement band for 60 seconds is also really, really exciting. I know Kendall is probably very excited as well, because that multi-messenger astronomy is her thing. Kendall, what do you think about today's announcement?
Oh, it's very exciting. This is something we've been looking forward to for a very long time. Being able to not only see it in the gravitational wave, so we can see inside of the neutron star, but we can also see what happens after they merge together with our instruments, our telescopes online. So it's been very exciting to see this story start to play out and come together.
Okay, so we'll go to our next question at Promote Science. Can two neutron stars collide and become a black hole? Well, I think the answer is pretty much a yes. Kendall, maybe you could say more on that, since you actually look at neutron star collisions.
So one of the ideas is that after these two compact binaries merge together, one idea is that you can form a black hole. there are other alternatives.
We lost Kendall.
Okay.
Okay, we lost Kendall.
We've lost Kendall. But okay, basically what goes to happen is if you have two neutron stars merging, there's two paths they can take. They can actually compact into one neutron star or a black hole. And I don't think we're 100% sure actually which one is the remnant from this event, but it is one or the other, but both are possible.
Exactly.
Okay, so we'll go to the next question. Alberto, less 1.6 solar masses is a lot for a neutron star. A total amount is closer to 1.4 solar masses. Can someone comment on this? Peter, would you like to make a comment?
So yes, I think we can have these. I think these neutron stars that we're observing merging here are within the range of neutron stars that we know about, within the mass range that we know about from normal electromagnetic observations. What I think is kind of interesting is what's the result of this merger? You know, is it a neutron star? Did they merge and form another neutron star? And if it is, then it would be one of the biggest neutron stars that we know about.
Or a very small black hole.
Or it could be a black hole, and in which case, yes, it'd be the smallest black hole we know. So either way, that's an interesting outcome. But we need to see more of these events and see what happens.
We need more observations, get more info. Okay, so Xin-Lun Cheng, how to confirm that the discovered EM counterpart is from the merging event that generated the gravitational wave, but not some coincidence? Well, I think it's like 1 in 20 million chance that they actually did come from two different events. So I think the fact that you had the gravitational wave burst, and I don't know how long was it?
So the
couple of seconds.
Yeah,
a couple of
1.7
seconds. Both coming from the same part in the sky. And all the statistics people who looked at this said, okay, that's 1 in 20 million, so we're pretty confident that they really did come from the same source.
And I think it sets a constraint on the speed of propagation of gravitational waves, right? The fact that they arrived, that they traveled 40 million light years and arrived within 2 seconds means that really gravitational waves and
they're a little bit faster.
But apart in 10 to the 15, very, very, very close to the same speed.
So they're not. It's not that they're faster than the speed of light. It's just that light can get scattered and reflected more. Gravitational waves are very pristine, very hard to knock them off their course, or really have anything really interact them.
But also there are processes within the actual astrophysics of the merger, I think, that Kendall probably can explain maybe a bit more. If she's back, she's back.
Oh, why they
why we might expect a separation of a couple of seconds between the actual the merger, where the gravitational waves are produced, and the light being produced.
Kendall?
Okay, so can you hear me now?
Unfortunately, Kendall's in a hotel room in Australia.
I think we still don't have Kendall.
I can hear you. I think connection was
okay.
Broke, but
okay.
she is there.
Okay, Kendall.
okay.
Okay, Kendall can be heard by YouTube, but not us. Okay.
Okay. So the idea is that what we see with the gravitational wave events is that we see the interaction of the stars themselves rotating and merging together. So that's the signal that we see. But what we see with the electromagnetic radiation is that once the stars merge together and of it starts mixing around, what we end up seeing is gamma ray production along these, that's within these jets that produces. So it takes time for that to happen. Once the two objects merge together, it takes time for the gamma ray emission to come out. And it's really exciting because with these two signals, it actually takes about, with this type of event, it takes about 2 seconds between the actual merger of the event and the production of gamma rays.
Okay.
Okay.
I have to apologize that we can't hear what Kendall's saying, but I understand everyone else can.
Okay, so hopefully Kendall explained everything very nicely there. Okay, so our next question is from Astro Clary. Could gravitational waves from the Big Bang be detected with the current instrumentation? Okay, can we throw up picture 201, if possible? Okay, so basically, if anybody didn't know, there is this idea when the Big Bang and everything exploded, I'm gonna run over here. So basically the gravitational waves when after the Big Bang happens and you had all the forces decouple, the current understanding is that because gravity is so much weaker, it might have decoupled earlier, actually 10 to the minus 35 seconds after the Big Bang, whereas the rest of them we didn't start seeing until 300,000 years. So when you see the cosmic microwave background, this is giving us a photo into 300,000 years after the Big Bang, which is insane, it's amazing. But gravitational waves will actually, okay, we're going over here.
Chasing us with a photo.
Gravitational waves will be 10 to the minus 35 seconds. So if you detect them, that's just insane information that we're going to be getting. Now, the current detector, LIGO, is this guy who's closest to me. That's the ground phase. So this is telling you what kind of sources they see and what they're sensitive to. The middle one is what we're expecting for space-based missions like the ESA-LISA mission, which is going to fly in 34. But then in the far, far left there, the yellow, that's the pulsar timing array sensitivity. And what you're seeing there, that big blocky yellow, is basically that they're going to see the stochastic background, because the stochastic background signal actually improves with how long you're actually integrating, how long you're looking. And the pulsar timing arrays, which are just listening to these neutron stars all over the universe, but like constantly and for years and years and years, and this is going to build up and build up and build up. And so we're really hopeful that those guys are actually going to see this. But for the moment, that LIGO won't be able to see it. Pulsar timing array, really hopeful. But there will be future detectors on the ground that may be able to see them. But just currently, it's not expected. Right now, we're just constraining. You know, we can say, okay, well, we know it's not this at this level. Okay, so hopefully that answers that question. Maybe we can take that picture. Take that picture down. Okay, why are there 2 seconds delay if the gamma ray and gravitational wave have the same speed as light? Oh, okay, I think we've already addressed that question.
Did we already address that?
Well,
I didn't hear Kendall's answer.
It's possible Kendall already addressed it.
I think Kendall answered that. Can we get the next question?
Yeah, so just in case. Yeah, just in case, it was the time delay between the merger event itself and which is what emits the gravitational radiation, and then once the event happens, there's a lot of particles mixing together and a lot of energy flying around, and things are moving very fast at 20% speed of light, something like that. And so that's the production of the gamma rays along these jets that are formed. So it takes time for that to happen.
Thank you, Kendall, for clarifying. Okay, so our next question is from Alman Srivastava. What can be other sources that can be detected by LIGO except merging black holes and neutron stars? Okay, well, I guess we've already mentioned the stochastic background, so this lovely, beautiful background that'll be coming from the Big Bang. But guys, do you want to comment on other?
So one thing that I know LIGO looks for is continuous gravitational waves emitted by spinning neutron stars. So if you imagine you have a star, your neutron star spinning, and if this is perfectly spherical, then it doesn't emit gravitational waves. But if it has a tiny, tiny bump on the side, everything changes. Then it starts emitting gravitational waves, and it actually emits gravitational waves at the speed at which it's spinning. So we know there are neutron stars out there that are spinning. Things like the Crab pulsar is a famous example. And so far we have not detected these gravitational waves. They should be emitted at a very specific frequency, and that frequency is not changing. So unlike the signals we see today that chirp up, this one should just be a continuous
but they're
signal.
They are weaker signals. They get stronger over
we don't
time,
know how
strong.
Yeah. We don't know. For now, all we're doing is setting limits on how strong these signals are, because we have not seen them yet. So we can say that these little hills on the neutron stars are small. Yes, exactly. But we keep looking, and the longer that we listen, the more chance we have of seeing these things. And the more statistics we build up, the better chance we have.
Supernovae.
Right.
I think we're hoping to see some of those, aren't we?
Yeah, those would fall under more of the unmodeled kind of events.
Well, there are people spending a lot of time modeling them. But yeah, we're still not entirely sure what that gravitational wave burst would look. So I guess that's the thing about these. You're also hoping to see something you're not expecting, like a huge blip in all the detectors at the same time. And then things are really going to get interesting. Okay, so next question is from Nazdi K. Which elements of the detector setup are most likely to be improved, and what will the effect of said improvements be, frequency, resolution, etc.? Okay, Ryan, since you're our on the ground LIGO guy, what can you say for that?
Yeah, so right now actually Advanced LIGO isn't operating entirely at design sensitivity, and that's in part because we don't have as much power as planned going into the detector right now. So the first one of the first next steps, I guess you would say, is to simply increase the power that we send in to the detector, which will increase our sensitivity. But then another method that we are looking to implicate in advanced LIGO is to do what we call squeezed injection, which is actually where we condition the vacuum state that we send in through this, what's called the dark port of the interferometer, and that we can use to reduce quantum noise in the detector. So those would be the two improvements.
Because the quantum noise that comes in on the much lower frequency or the higher frequency?
Quantum noise couples in two ways. So there's quantum power fluctuations in the arm cavities in these high finesse optical resonators, which actually move these test masses, which you read out as differential position noise in the dark port. But then there's also a counting noise at your output, which is just it's a photon counting noise that's referred to as shot noise. So these two couple into the detector in different ways, and what we do essentially is we condition the vacuum state that we send into one of the ports of the detector to reduce this quantum noise.
And what we have beside us here is actually the sensitivity of those detectors.
Yeah,
so
yeah.
Where would we be going lower? Would we be like lowering it here, in the middle?
So if we do what's called frequency-dependent squeezing, we'd be able to sort of reduce basically throughout the detection band of the
whole
detector.
Thing comes in. Okay, that'll be very cool. Okay, so we'll go on to our next question. Why are LIGO and other detectors in the L-shaped arrangement? Oh, I can take this one.
It's a nicer question, and we can draw on our board as well.
Question, and I can draw on our board. Okay, well, basically, if you have a gravitational come true, so if a gravitational came just straight through us right now, and say there was a circle here, and here, and here, and here, well, basically what happened is these, what we like to call test masses, are going to be distorted. This is highly exaggerated. Something like this, and then it'll go back to its circle. I'm running out of space. And then it's actually going to go really, let's go up here. It's going to go like fat. So I guess basically, like if you were looking at me, I would go tall and skinny and fat, kind of like that. And so when you're trying to actually measure this, the best way is ideally you kind of think of your interferometer like that. And when this gets squeezed, this guy's going to get a little bit longer, and this guy's going to get a little bit shorter. And if you send a ray this way and a ray that way, and when they come back, you impose them on each other to see the difference. And basically, you do it in a way that they should cancel each other out. But if this guy's gone a shorter distance and this guy's gone a long difference, this is going to shift them. And that's why. So this is kind of, and that's what tells you that there's the gravitational wave there. So ideally, we do the right angle because that's actually the polarization of the gravitational wave. It's how it'll change the masses in the maximum way. Now, obviously, if the gravitational wave comes from a different direction, then you don't have as much displacement, but that also tells us more about actually the directions. So that's basically why. Okay, so our next question. How do you combat various noise sources in the experiment? Okay, okay, Ryan, I think we'll throw back this one to you since...
Yeah, so there are a lot of different noise sources in this experiment. What we're trying to measure is a very small average change in position of these test masses. And so really any sort of environmental effects on these test masses is also going to be read out in the detector. The short answer is that we have hundreds of thousands of environmental monitor channels that tell us what's happening at all points throughout the detector. And in particular, so one big problem is movement of the test masses themselves that's not caused by gravitational radiation. Right? This detector will read out any sort of movement, whether it's caused by emerging black holes or things moving overhead, ground shaking. So what we do is we put these test masses on pretty complicated suspensions, which attenuate that motion due to ground motion. There are other sorts of noises, though, that we can't really attenuate with suspensions, such as what's called gravitational gradient noise, which is, if something super massive were to just move by our detector, and pull on these masses just so slightly and move them, there's no good way to shield that except to maybe go very, very far underground. And that's something we'd have to just measure and subtract out.
And that's actually what the Japanese future mission, our future detector is
so
going to be.
Yeah, so Kagra goes underground, which helps mitigate problems with gravitational gradient
And also
noise.
some of the noise I heard when they first started operation, like in Livingston, Louisiana, no one had thought about the fact that it was their hunting ground, so people accidentally shot the detector.
Yeah. So one of the LIGO detectors is in Louisiana, and in Louisiana, there's a lot of hunting. And so
I love that no one thought of this.
Yeah,
we
so
can figure out that planes are going over.
it's not something
masses,
you generally consider when you're building a science experiment. Is how often is this going to get shot at?
Okay, we'll go on to our next question. Okay, our next one is from George Dishman. How will this observation assist in determining the equation of state for a neutron star core material and particles beyond the standard model? Okay, Kendall, I think you probably want to grab this one.
Okay, yeah, so, well, to determine the neutron star equation of states, there's a lot of complicated physics that we are still uncovering and discovering right now. But what we can do with this recent detection is determine which models would not be appropriate. So what we would need to do is just generate a lot more of these types of events, and then we can do more modeling of what we would expect of the gravitational waveform to look like for these types of things and try to narrow it down that way. So we can start to rule things out, but it's still a very large unknown as what's actually happening inside of the neutron star.
But would more of these detections help?
Yes, sure. It would certainly help. It would certainly help to identify the different gravitational waveforms that would produce such events. So, yeah.
Okay. Thank you, Kendall. Okay, our next question is from Rajat. What are the other projects and objectives of LIGO in the near future? What are the long-term ambitions? Any collaborations planned? Okay, so, well, I guess LIGO's continuing to, it's shutting down now for the next year, isn't it, as they upgrade?
Yeah, well, so Advanced LIGO goes through stages of observing runs and then shutting it down, doing minor improvements, things like this, and then continuing to do observing runs. So the second observing run, which is where we saw this event, is on the tail end, is over, actually.
But how many observed? So we're done with the second one, but there's 5 planned or something, is it?
So, yeah, that might be contingent upon
funding.
Other things. But
okay, but I think we're good for up till 2019. There's going to be just breaks where we're going to improve the detectors.
Yeah, periodically we'll take data and then shut down.
And simultaneously with Virgo as well, they'll be shutting down. And
right, and
everyone's trying to kind of be
ideally there'll be a lot of overlap in the time that they're actually observing.
And then further on, we want to build another LIGO in India. Is that right?
Yeah. So then the next stage is building another LIGO in India. Then the one in Japan called Kagra will soon be online, and then the far future, I suppose, people are looking into larger ground-based detectors.
Like Cosmic Explorer and the Einstein
Cosmic
Telescope.
Explorer, Einstein Telescope,
okay.
And these are all...
And let's not forget
Yes,
space.
and
so in 2034, I think ESA has said that they're going to launch a space-based one. So that's what we've got a little picture of over here, which will be 3 spacecrafts that will act like 3 interferometers bouncing lights around the place. And then that will be able to actually, can we throw up actually that picture? When you have the space-based and the ground-based, you're going to get some really nice stuff. Oh no, we don't have the picture up. But basically what you're going to be able to see is, like, people worked out, like Alberta Susanna in Birmingham worked out that if LISA had been operational for that first detection, LISA would have seen it 2 years ago, and they would have been able to tell the ground-based people, hey lads, yeah, here. No, that's not the one I was talking about. But basically, LISA, which is the blue. But basically, the waveform would have gone through the LISA band into the LIGO band. So LISA would have seen it 2 years beforehand, been able to tell LIGO, lads, in 2 years you're going to see this. Don't be in an engineering one. Really pay attention. So once you get space involved as well, and there's so much more physics you can do if you can track that same one. People have showed, like, you can reduce things like constraints you're putting on alternative theories by like factors of 10 and stuff by just following the same signal through both bands. So that's really going to get exciting.
That's right. I mean, the key thing about going into space is that we get away from all the noise on the ground, okay?
Gunshot fire.
Exactly. There's no one shooting guns up space, hopefully. Okay, and so, yeah, you really open up a new frequency band, much lower frequency, slower signals. And so you're seeing systems that are not merging, they're just continuously emitting gravitational waves. So rather than the bursts we see with LIGO, they're really just emitting all the time, and you hopefully, when LISA turns on in the 2030s, you just hear a cacophony of gravitational wave signals all superimposed, and then we have to try and work out where they're all coming from.
Yeah. Okay, so next question. Why do you use infrared laser beams? Ryan, I think we're going to jump back to you.
Yeah, we're heavy on instrumentation. So while it is true that if we were to use shorter wavelength laser light, we would be more sensitive because what we're measuring, right, is the interference of these laser beams, and we use 1064 nanometers, which is right above a little bit out of the visible range. And we use it because we have good lasers at 1064, and because we have good optical materials and we understand them really well.
So everything needs to be incredibly stable for this experiment, right? You need the best and most stable of everything you can.
Right.
So it's basically the ones we have the most expertise on.
We have a lot of expertise in them, and yeah.
They're stable. Okay. So next question: what will future additional future detectors of neutron future detections of neutron star binaries tell us? Kendall, I guess we're going to jump back to you. If we did see lots and lots more of these amazing detections continue to happen, how can we? What's that going to tell us about the science?
So there's a lot to be uncovered in this case. There's a lot of interesting and fundamental science that will be uncovered.
We're going to have to stop you, Kendall. We're going back to...
We're thrilled to have a distinguished...
We're going back to Washington now.
To describe a wide-ranging set of observations of the event you heard about earlier this morning. For many decades, astronomers relied on light for their observations of astronomical objects. First visible light, then radio waves, then infrared, X-rays, ultraviolet, and gamma rays. More recently, observations of particles such as neutrinos, and now observations of gravitational waves have been added. As you heard several times in the first panel, we use the term multi-messenger astrophysics or multi-messenger astronomy to refer to the detection of light, particle, and gravitational carriers of information about astronomical events. Now, focusing in on the messenger that we call light, large groups of astronomers around the world have been involved in the observations of the August 17th event. As mentioned earlier, the event reported today was the first ever involving both detections of gravitational waves and of various forms of light. After the source of gravitational waves was localized, there were 6 independent discoveries of the flaring optical counterpart, often referred to as a transient source because of its rapid brightening and fading. Those discoveries were spread over a period of less than an hour. Most of the optical discovery teams are represented here today, as well as teams observing the transient source using X-rays and radio waves. And you had a question in the first panel about the robotic strategies, and you'll hear about different strategies for honing in on the optical source from this panel. It's not one size fits every telescope. So you'll hear about observations involving major telescopes funded by the National Science Foundation, orbiting observatories funded by NASA, other major telescopes supported by other national agencies, by universities, by foundations, by other independent groups. And these have been used by a host of talented astronomers, funded by federal agencies and by other institutions. So each brief presentation that you'll hear by one of these speakers is worthy of an entire press conference. We hope this event encourages you to follow up and speak with the presenters at more length, to follow up as this story unfolds over the weeks ahead. There are dozens, if not hundreds, of research papers already submitted or nearing submission. You heard earlier about 70 observatories and 100 instruments. Well, the overview paper on the light detection is being published today in the Astrophysical Journal Letters, and it has over 3,500 authors. That's 3,500. So I think the author list is longer than their page limit usually is, so I don't quite know what they're doing about it. I'd also like to recognize we have in the audience Dr. Roger Blandford of Stanford University. So he chaired the 2010 National Academy's Decadal Survey in Astronomy and Astrophysics, so he'll also be available to discuss the significance of these observations with the press. And now to the first speaker, Dr. Laura Cadenati, Deputy Spokesperson of the LIGO Scientific Collaboration.
Thank you, Jim. What you've heard today is the news of a discovery that has opened a new era of gravitational wave astronomy. What this means to me is equivalent to the transition from looking at a black and white picture of a volcano to sitting in a 3D IMAX movie that shows the explosion of Mount Vesuvius. You are surrounded by the flashes of lights and engulfed in the sounds of the volcano fury. So that's what it means to me. The combined information of gravitational wave and light is bigger than the sum of its parts. From the combined information, we are learning new things about physics, about the universe, about the elements that we are made of. And no one has ever done this before. What we heard this morning is something that happened some 130 million years ago, back when the dinosaurs were roaming around Earth. In the Hydra constellation in the southern hemisphere, two neutron stars that have been dancing around each other for millions of years got close and collided. In that final embrace, they produced a fireball, an afterglow of light. They ejected neutrons that produced radioactive reactions. All of this happened, and 130 million years later, on August 17, LIGO and Virgo felt the early tremors of space-time in our detectors. About 2 seconds later, Fermi and Integral got the first photons that were coming from the gamma-ray burst that was simultaneously produced. So this by itself is already a groundbreaking discovery. It's the first evidence that binary black hole coalescences produce short gamma-ray bursts, and the confirmation that light and gravitational wave travel at the same speeds as Einstein had predicted. So this was groundbreaking, but it's only the beginning of a story that my co-panelists are going to be telling you in detail, and that's an amazing story. What I wanted to tell you are just two things that we could learn from the gravitational wave messengers, and they are part of this story, and open also new branches of science by themselves. So the first one has to do with the universe. The universe has been expanding since the Big Bang, and the bigger it gets, the faster it expands. The Hubble constant is the quantity that sets the scale for this expansion. And astronomers have been trying to pin down this number for more than 80 years. There are different measurements that are not too far away from each other, but not in comfortable agreement quite yet. What LIGO and Virgo have done using this latest data is to introduce a new method, completely independent. This is a method that was first proposed 30 years ago by Professor Bernard Schutz, who's here in the audience with us today. And the idea is to use the signal, the gravitational wave signal from the two neutron stars to measure its distance from Earth. And so now we have a new yardstick, a new standard siren that's going to allow us to measure the expansion of the universe. So welcome to the new era of gravitational wave cosmology. I want to tell you also something else that we can learn from the gravitational waves. So you're going to see now in this movie, this is not an artistic rendition like the previous picture you saw was. This is a computer simulation, an accurate simulation that uses general relativity, magnetism, hydrodynamics to study simultaneously the motion of matter inside the neutron stars and the gravitational wave production. So you see on the left, the two stars that are clashing on each other, they're ripping each other apart and throwing matter around. And at the same time, you see the gravitational wave that's been emanated. And now by looking carefully at the gravitational wave signal that's produced in our detector, like the chirp you see in this graphic, we're going to be able to understand the properties of the dense neutron star matter. And so already from our findings, we can already constrain what's called the stiffness of the neutron star, how stiff it is and how large it can be. And these are new constraints that we are setting. We are confirming some of the predictions that were done by X-ray observation, but these are done in a completely independent way. And this, moving onwards, is going to be allowing us, with the discovering of new of this system, to put tighter limits and information that's going to be important not only for astrophysics, but also for nuclear physics. So we have cosmology, astrophysics, nuclear physics, newly informed by gravitational waves. This event is really a gift that keeps giving. And all of this has been possible by having LIGO and Virgo observing together and by the collaboration with the worldwide electromagnetic observational community. So this partnership around the world is what has made possible the story that you're going to hear next from my colleague in the panel. And we're going to start with Andy Howell, who's going to tell us what happened in the first 12 hours leading to the identification of the optical counterpart.
Thank you, Laura. A long time ago, in a galaxy far, far away, two neutron stars merged together, but we only found out on Earth on August 17th, right before the solar eclipse, and we've been keeping this secret this whole time about the bust. This was really exciting because neutron stars are the hardest thing in the universe, harder than a cue ball, harder than a diamond, and we really wanted to see what would happen if you smashed two of them together at near the speed of light. Neutron stars are like a giant atomic nucleus, only one 10 miles in diameter and composed entirely of neutrons. So this is like a cosmic scale atom smasher of energies far beyond humans will ever be capable of building. So when they smash together, theorists told us that you should get these little chunks of stuff flying apart that are basically atomic nuclei bathed in the sea of neutrons, and that's how you get the neutron-rich heavy elements on the periodic table, like gold. So they basically said, up in the sky, there is a giant explosive train wreck that makes gold. So this produced the exact reaction you might expect, the astronomical equivalent of stopping traffic while we all stopped to go and get a look. And the problem was they could only tell us the position to within about 150 times the size of the full moon. So that's the astronomical equivalent of over there somewhere, which was still way better than the state-of-the-art previous, which was, it's kind of hard to say where it is. So another problem is that it was only visible for about, that position was only visible for about an hour each night, because it was in a setting field near the sun. So astronomers scrambled to get observations, and about 11 hours after the merger, the SWOPE supernova survey really hit the jackpot and found the first evidence of an optical transient called a kilonova, an amazing explosion associated with this merger of two neutron stars. 6 other teams around the world had independently detected it before the first announcement. Our team at Las Cumbres Observatory, led by Dr. Yair Arkabi, found also some evidence of this explosion. It was initially called SSS-17A by the SWOPE Supernova Survey, but it was eventually given the name AT 2017 GFO. AT stands for Astronomical Transient. I know it's a boring name, but it's just some automatic name that it gets. We started everyone started announcing these on these circulars that we send to each other, and astronomers around the world scrambled to get observations. So at our, if you're at a ground-based observatory, you have a disadvantage in that you have to wait 23 hours to be able to observe the kilonova again. But at Las Cumbres Observatory, we've built a global worldwide network of telescopes, and they're robotic. So the idea is we get an alert, and we have software that parses it and figures out the best galaxies to observe in that region and makes a list and sends it to our telescopes and schedules the telescopes. So humans don't even have to be involved. We actually were in this case because we were super excited. We want to make sure everything goes okay, but it's a new kind of observing. The idea is you distribute telescopes all around the globe so it's always dark somewhere, and then as the Earth rotated, we could watch it multiple times. So we saw it first in Chile, and then as it got dark in Australia, we saw it again, and then again in South Africa. So every 8 hours, we were making observations. On the screen here, you can see the initial detection by our group, at least. The red is the Fermi localization region. Then the blue is the LIGO and Virgo localization region. And then there in the inset, you can see the kilonova right there in the galaxy, NGC 4993. Once we started getting data coming in from all over the globe, you can see the sites that are listed up in the top here. We noticed that it brightened to 200 million times brighter than the sun over the course of a few hours, and then it faded very quickly over the next few days, faster than any other astronomical transient that's so bright. It started off blue, and then it turned red over time. We also got spectroscopy, that research led by Dr. Curtis McCulley. We got data from our own spectrographs in Australia, also the SALT telescope in South Africa, and the Gemini telescope in Chile. Our data was mostly in the optical, and later on, as we'll hear from other panelists, they got data in the infrared as well. There were some surprises. It was very much brighter than we expected early on and much bluer, but we thought that the heavy elements would block out a lot of the optical light. But it turns out maybe the heavy elements were buried. Their signatures did come in a little later, and when we split the light up into a spectrograph, when we split the light up into a spectrum, you create a rainbow. And so they did see the signatures of the heavy elements then, so there really was a pot of gold at the end of a rainbow, at least for a kilonova rainbow. The other thing I would say is that we finally now know what happens when an unstoppable force meets an immovable object, and the answer is a kilonova. So if there's more, we've made a video explaining this discovery that you can find at lco.global. Explains a little bit more about our observatory. But next up, we're going to hear from many of the other observatories who detected the event and about some of the astrophysics they found. First up is Ryan Foley from the SWOPE Supernova Search Team.
Good morning. I get to tell you the story of how our team originally found this object. On August 17th, I was trying to take a well-earned afternoon off when my graduate student Dave Coulter sent me a text message saying that LIGO and Virgo had detected a binary neutron star merger and that there was an associated gamma ray burst. I thought it was a practical joke and he was trying to ruin my afternoon. But after some convincing, I realized that it was real, and I quickly rode my bicycle back to the university where my team was preparing for our observations that night. Working with astronomers at the Carnegie observatories, our NSF-funded team uses the SWOPE 1-meter telescope at Las Campanas Observatory in Chile. This was in Chile, and it took a little while before the sun was going to set, and during that time, we created a prioritized list of galaxies to search for the light associated with the gravitational waves. Soon after sunset, we started observing. In our 9th image, we observed this galaxy NGC 4993. Comparing our image here, showing the galaxy, comparing our image to images that were taken a year earlier, we found a new source, which we call SWOPE Supernova Survey 2017A, or SSS-17A, indicated by the arrow. This is the kilonova that people have been talking about. UC Santa Cruz postdoctoral fellow Charlie Kilpatrick was the first one to see it, and when he did, he told me simply, in his understated way, found something. Of course, it wasn't just something. Charlie was the first human to ever see optical photons from a gravitational wave source. And this image here, that on the screen, is the first image of a gravitational wave source. So this precise position within this galaxy enabled both our ability to see the birthplace of the gravitational waves, and later allowed other observatories to do targeted follow-up observations that some of the other panelists will talk about later. Also, in this one instant, from this image, a new scientific field was born. We were finally able to take two of the four fundamental forces, gravity and light, combine them together to reveal something about the universe. Gravity through the gravitational waves and light, and electromagnetism through light, we were able to finally solve some of these mysteries. Now, our team, we got lucky, but luck favors the prepared, and we were ready. When we made this discovery, we quickly announced it to astronomers around the world. Meanwhile, our Carnegie collaborators used the twin 6.5-meter Magellan telescopes to get additional images and spectra, and that provided crucial color information. Within the first 24 hours, I used our initial data to determine that there was roughly a 99.999% chance that the gravitational waves came from the SWOPE source. Over the next few days, we saw the object fade and turn from blue to red, confirming that the source was indeed the light from the gravitational wave source. And with that, I'll pass things on to Dr. Marceli Suarez-Santos.
Good morning. So the challenge that we face every time that the LIGO collaboration issues a new trigger is the following. How do we search for an optical source that is rapidly fading, was possibly faint to begin with, and it's localized somewhere over there? It is the classical challenge of finding a needle in a haystack, with the added complication that the needle is fading away and the haystack is moving. So how do we approach this challenge? In our case, our team is fortunate to have the dark energy camera, which is a wide field of view camera installed on a large telescope, the NSF Blanco 4-meter telescope located in Chile. This telescope and camera system allow us to search large areas in a short period of time. In other words, it allows us to search the entire localization area of an event and allows us to determine where the source is located. In this case, what you're seeing here is the localization map as seen from the vantage point of DCAM in Chile, just at sunset time that day. As you can see, the region of interest, now that I'm showing what it is, it looks easy to find. But our strategy here was to use this wide field of view camera to map out the entire region multiple times with overlapping exposures so that we could find the source even if it were 10 times further away than this particular source was. This enables us to determine what is the optical counterpart and enables ultimately to perform a number of scientific endeavors. The closest to my heart is cosmology, which is the goal of the Dark Energy Survey and my own in terms of science. Well, this camera, I have to say, is also a topic of pride for me because I helped build this camera. It is an incredible pleasure to be able to do this beautiful science with an instrument that I helped build. Well, our strategy, as you know, paid off handsomely. Not only we were one of the first teams to be able to independently discover the source, but also we were able to rule out 1,500 other candidates that were present in that haystack. Truth is, things that look like needles in this haystack are very common, and it's the problem here is not only to find a needle, but to make sure that we have the right one. And today we are certain that we have. So now I'm going to pass the mic to David Sand, who's going to tell us about the strategy that his team employed.
Good morning. The strategy our team employed to identify the optical counterpart is a straightforward extension of what we do every night, 365 nights out of the year, as part of an NSF-funded program to find very young supernova in the nearby universe. We operate a small, robotic, 16-inch telescope. It's basically a souped-up amateur telescope, which sits on a mountaintop in Chile. Its name is Prompt, and it was developed at the University of North Carolina. With the telescope, we normally observe 500 galaxies a night that are within our local universe, or within about 140 million light years of Earth. We look at these galaxies night after night after night in the hopes of catching supernova when they're very young, just after they explode. Whenever a gravitational wave alert is issued, we cross-match the localization on the sky with our galaxy catalog and boost the priority of those galaxies to the absolute highest priority. As we have heard, we knew that GW 170817 was potentially a special event, And so we spent the extra time before Chilean nightfall working on our telescope scheduler, making sure that all the galaxies get observed because they were very close to the horizon and setting. In total, we looked at about 20 galaxies within the LIGO Virgo localization, spending about a minute on each, popping them off one at a time. Everything in our program is automated, and there's almost no human in the loop, thanks to the development efforts of Dr. Stefano Valenti and his graduate student Sheng Yang at UC Davis. We knew very quickly that NGC 4993 had an interesting transient event within it, because we had observed the same field 20 days earlier, and our software flagged it and alerted our team. You can see that here on the screen. The image on the left is the image we took 20 days before the gravitational wave event. The image in the middle is our discovery image, and the image on the right is the difference between the two. The only thing that's left is the kilonova. At the click of a button, we were able to get a second observation of the field to confirm that what we saw was not a glitch or an asteroid, but was indeed a new object in the night sky. And we alerted the community, just like the other teams up here and others around the world. Even with just our small telescope, we could tell that this transient was unique in nature because of its quickly fading properties. This program has a bright future. Okay? We could detect this kilonova event even if it was twice as far away with no adjustments to our program. And so small telescopes can still play a large role in the coming era of multi-messenger astronomy. Next up is Dr. Neil Tanvir.
So, what happens when two neutron stars collide? You've heard that these are incredibly dense objects. They're being smashed together with huge velocities, with huge violence. Material is thrown out. It creates a highly radioactive fireball. And in that fireball, new elements are synthesized, are created. But that's the theory. The question is, do we believe the theory? Is the theory right? Can we test it in some way? So, having found the counterpart, as you've heard about, the next stage, the high priority then, was to make intensive observations of that source so that we could gather all the data that would be required to test the theory. And I have to tell you, we've done a lot of work on that. I think that's going to carry on for months and years into the future because of the richness of the data set that we've managed to gather, which really will help us sort of dissect the explosion and test these really complicated, difficult theories for the first time. Now, we were helped because many of the world's most powerful telescopes are based in the southern hemisphere, particularly in Chile, and one particularly important part of that is the European Southern Observatory, which operates some of the world's largest and most sophisticated state-of-the-art telescopes at several sites in Chile. And in fact, several teams of astronomers were involved in using no fewer than 14 different instruments on 10 different telescopes at ESO to make these observations. And we think that makes it the largest and most complicated campaign of astronomical follow-up that's ever been conducted. It's certainly over such a short period of time. Now, a key aspect of this campaign, which you've heard a little bit about so far, is that we wanted to observe not just in optical light that our eyes are sensitive to, but also in infrared light, the kind of light that you would see, for instance, with night vision goggles. And actually, as it happens, that my own team was the first to make an infrared observation within a few minutes of the optical discoveries using the ESO's 4-meter Vista telescope, which is the most powerful wide-field infrared telescope in the world. Why is there interest in the infrared? The reason, it turns out, is because as the material billows out from the explosion at very high velocity, the prediction is that that should start to act like a kind of smoke screen, blocking out and locking in the optical light and causing the optical light to fade away quickly, as you've heard other speakers tell you that they saw. On the other hand, in the infrared, and the near infrared is the technical term, we expected a much longer-lived event. Okay, so how did the theory do? Let me show you what we saw. And you can see in this movie, hopefully, and it'll repeat again so you'll have another opportunity to see it, a time-lapse movie of about 3 weeks of observations. When the transient first switches on, it comes up very rapidly in brightness and is very blue there. As it fades, it turns quite a deep red and then disappears into the light of the galaxy. So I would say, in fact, that the theory seems to have been doing pretty well. Of course, as scientists, we like to put things on charts as well as watch movies. And so if I put that data in a chart, you'll see the blue points there indicate the optical light fading quickly away. But the red points are the infrared light. And as we monitored that over many days, we saw that it remained bright almost for a week before it really started to fade away. So I think the theory passed this particular test with flying infrared colors. Now, it's by very careful analysis of data like this and like the spectroscopy that we have confidence now that heavy elements are being produced in this explosion, this kilonova explosion. Although we don't see directly the signatures of gold and platinum, the fact that we see the evidence for for very heavy elements being formed tells us that the conditions were right in this explosion, and we're very confident, therefore, that all of these other heavy elements must have been formed in the same process. What happens to this ejected material? It's flying out at very high velocity. Of course, it's going to quickly start to mix in with the other gas within the galaxy, NGC 4993, and gradually get diluted, and maybe in millions of years condense again into new planets and stars in that galaxy. So that's a very intriguing thought. It suggests that billions of years ago, in our galaxy, the Milky Way, similar mergers must have happened, and that they likely created these rare, precious metals, such as gold and platinum, that we find in deposits in the Earth today. So to tell us more about the implications, I'll call on Ido Berger.
Good morning. Following the identification of the visible counterpart, about 12 hours after the LIGO detection, as we heard from the previous speakers, several teams, including my own, commandeered the most powerful US, NSF, and NASA-funded telescopes on the ground and in space to study the detailed properties of the merger event. The plan was simple: capture every single photon of light from this event to uncover all of its detailed physical processes, as we can see in the movie that's playing behind me. But the challenge was quite severe. The light was fading away rapidly, in fact, much faster than any previously seen type of cosmic explosion. On mountaintops all over Chile, telescopes veered into action. We took images of the fading visible light every night with a dark energy camera on the Blanco telescope until the source faded from view about 10 days later. Nearby, the SOAR telescope dissected the visible light to produce spectra of the radiation. The Gemini telescope produced images and spectra in infrared light in exquisite detail. Together, they revealed details that we've never seen before in any astronomical events. The direct fingerprints of the heaviest elements in the periodic table: gold, platinum, uranium, and other rare elements. In fact, from the properties of the visible and infrared light, we conclude that the total mass of all the heavy elements produced in this one single event is 16,000 times the mass of the Earth. Of this material, we estimate that about 10 times the mass of the Earth is in gold and platinum alone. So imagine this as you gaze at your jewelry or going to invest in gold futures. But even more important is the realization that as this material is flying out from the site of the two neutron star merging, they will eventually combine with other material to form stars, planets, life, and jewelry. So while this information was being gathered from telescopes on the ground, in space, the sharp eye of the Hubble Space Telescope was brought into focus on the same location of the sky. Over several weeks, the Hubble repeatedly obtain ultraviolet, visible, and infrared images of the merger event. In this beautiful Hubble image behind me, we can see both the counterpart of the gravitational wave source in the red circle and its home, the galaxy NGC 4993, in magnificent detail. And these images are not only pretty, they allow us to explore a completely different facet of this event. How did a system of two neutron stars actually come into being, and how long have they been orbiting around each other before the final cataclysm that we saw on August 17? So while most of the observations were focused on the aftermath of the event, the Hubble data allowed us to peer back to the beginning of the source. Think of it as kind of like CSI NGC 4993 edition. So stretching this analogy, we use astronomical forensics techniques to find that the two neutron stars formed in massive supernova explosions when the universe was only 2 billion years old. So they have since spent all of cosmic history, 11 billion years, in a decaying orbit around each other until they finally collided and merged on August 17th. So I would like to leave you with a parting thought to ponder. The supernova explosions that gave birth to the two neutron stars in the merger system produced and expelled all of the heavy elements up to iron and nickel. Then 11 billion years later, the collision of the two neutron stars completed the production of the heavier elements in the periodic table, up to uranium and even beyond. So in this one system, we see the complete history of how the periodic table of the elements came into being. Thank you. And now to discuss the X-ray radiation, Eleonora Troja.
Hi, everyone. So as you heard, for over a week, astronomers were amazed and excited by the discovery of the kilonova, which solved the mystery of the heavy metals. But at the same time, we were scratching our heads to solve another enigma. Where had the X-ray light gone? Every time that we observe a gamma ray burst, and we observe hundreds of them every year, we also see its fading glow in X-rays, optical, or radio. And this time, we were not expecting things to be any different. As you heard earlier this morning, Fermi detected a standard short-duration gamma ray burst. And we were expecting the standard behavior at lower energies, including X-rays. So for this reason, 3 NASA missions, SWIFT, NuSTAR, and Chandra, immediately pointed their telescopes to catch the X-ray light. SWIFT was the first one to arrive on target. And imagine the surprise when SWIFT reported a bright source of ultraviolet light, but no X-rays. In 13 years of SWIFT mission, that was the first time. NuSTAR and Chandra also came empty-handed. So the lack of X-ray signal immediately told us that something unusual was underway, and something like we had never seen before. So at that time, it might have looked like all the fun was in the infrared. Yet we did not give up on the X-rays. And we decided to keep looking for the X-ray light to turn on. My team decided to use Chandra to look at the kilonova one more time. We knew that there was a chance for the X-ray light to turn on at a later time, but it was slim. So for us, it was like buying a lottery ticket. 9 days after the LIGO alert, Chandra performed another observation. And that's when we saw that the X-ray light had just turned on. And it was amazing. This newborn signal was way too faint for any other X-ray telescope, and Chandra was the only one that could possibly see it. And the low expectations of success made this discovery even more incredible for us. So the image that you see on the screen is the X-ray image that revealed the presence of an X-ray signal. The bright spot that you see at the center of the image is the galaxy nucleus. And the blue dot that you see within the box is our source. It's the first X-ray signal from a gravitational wave source. So what does this X-ray signal tell us? Well, it tells us that beside the kilonova, with all its bling, something else just as exciting was underway. Very likely, the collision of two neutron stars resulted in a new black hole. And this black hole ejected a high-speed jet of energy and matter. So this jet was carrying the same amount of energy that our sun radiates over millions of years. And it was expanding with velocity close to the speed of light. The reason we had to wait 9 days before seeing the X-ray signal is because this jet was not pointing toward us, but it was coming at a slight angle. So the idea that we could see emission, light, from an angled jet is nothing new. It has been floating around for 20 years, and for 20 years we had been looking for proof. And now, all of a sudden, here it was. This was mind-blowing. Not only did we see the first X-ray signal from a gravitational wave source, but we also proved a theory that had been in the waiting for 2 decades. Unfortunately for us, after a few days, the sun came in between us and the source, and observations with Chandra were no longer possible. So my colleague, Alessandra Corsi, will tell you what happened next.
I have one last surprise to report about this fantastic story. Even though radio was late to the party, it will be the last to leave. It took 16 long days for the faint radio glow from this cosmic smash-up to turn on. All we could see before day 16 was the bright radio emission from the faraway galaxy that hosted this merger, as you can see in the right panel in this figure. After holding our breaths for so many days, Greg Hallinan and I independently spotted a new dot of radio light in images taken with the Jansky Very Large Array, a facility of the National Science Foundation. Capturing this radio emission early on required the sensitivity of the Very Large Array, a radio telescope array 1,000,000 billion times more sensitive than a cell phone receiver. Also, the VLA sharp view proved that the radio was coming from the same exact sky location as the visible light. After turning on, the radio emission has grown brighter and brighter. So in the central panel, you can see how it looked 23 days after the merger, that little dot of light marked by the crosshairs. As we speak, several teams and radio telescopes around the globe are continuing to monitor this source. This includes our own growth team, a global relay of observatories watching transients happen. Like the X-ray result described by Eleonora, the delayed turn-on in radio supports the idea of an off-axis jet. As you can see schematically from the left panel, this jet drilled through the neutron-rich debris and formed a slower cocoon. After breaking out of that debris in a flash of gamma rays, the jet raced through the interstellar medium, the gas and dust between the stars. There, it powered radio emission that here on Earth, we happen to be observing from an off-axis perspective, like shown by that eyeball in the left panel. After 20 years of searching, we have caught the first off-axis jet from a double neutron star merger. Like with a tilted flashlight, now we can see behind the main beam and take our very first view at the cocoon. The radio data, in particular, are unfolding the story of how the jet and the cocoon interact with their surroundings. As we continue to monitor the source over the next months, possibly years, we're going to learn how much energy was imparted to the cocoon and unveil the properties of the interstellar matter that is being engulfed and shocked by that jet. After all other wavelengths have spoken, radio gets to be the tiebreaker between theoretical models that we can only now test directly. I would like to end by saying that in this fantastic event, gravitational waves and light at all wavelengths have given us an amazing multisensory learning experience in the study of the universe. Welcome to the era of multi-messenger astronomy.
So now you see why we needed two panels, and I want to acknowledge on behalf of the 15 people we've had speaking on the two panels, the thousands of people in the LIGO scientific collaboration, and in the many, many teams across the electromagnetic spectrum that were involved in these discoveries. I invite questions from you. If you have a particular speaker you want to direct it to, feel free. If you're not quite sure, we'll try to get it to the right person. And please wait for the mic so that the webcast can hear you. Okay, let's go there first. And then
Seth Borenstein, Associated Press, for any of the panels who want. I assume, is it fair to say that without LIGO Virgo, you wouldn't have had this giant multi-spectrum analysis over electromagnetic radiation? Is there, I mean, how important is it to get all the different spectra on the same object? Has there been something similar, minus gravitational wave, any similar one event that gets gone through if you didn't have the gravitational wave?
So Ido, why don't you take that, since you've been doing gamma ray bursts for a long time?
Yeah, so I think it was critical to know where to look. As you heard, this event, the light fades away extremely rapidly, and if we were just searching for it blindly across the whole sky, we would not see it. So LIGO telling us where to look was extremely important. In terms of the intensity of observations, I don't think there's been anything like this before. Perhaps the closest analogy that people have been talking about is the supernova in the Magellanic Clouds in 1987. But here we have a much larger number of observatories and people involved and exquisite level of data.
Okay, I had a question over here.
Really short questions followed by another question. Really short question is, in all the photos that shown the image of the galaxy and then the dot, how bright is that galaxy relative to other stars? And then the other question is, since it still took about an hour between the gravitational wave detection scopes were alerted, is there any critical information that someone like the telescopes could have observed otherwise, according to theoretical models?
So, Andy, why don't you take it first, and then I'm going to ask Neil also to comment.
I can take the last part. It was actually about, I think it was something like 5 hours until the alert was issued, but then we also had to wait for it to be observable in Chile. If we had gotten the alert earlier, we have this robotic network of telescopes that are all controlled by a central place in Santa Barbara. We could have started observing in, say, South Africa, or at least in South Africa, if not earlier. So we could have caught it even earlier. So we just don't know what happened in the first 11 hours. So that would be a great mystery to explore when these things are going to happen again, and we'll be ready, we hope. For the brightness, I'm not sure exactly how bright it was.
I'm not sure exactly either, but I just did a quick calculation in my head, and I think it's about 1,000 times fainter than you could see with the human eye. So it's it's pretty faint, but of course with modern telescopes that's relatively straightforward. For the galaxy, yeah. The other question I'll comment on briefly. So you asked, if we could have filled in the gap in those first 12 hours, what might we have learned? And I think one of the things that perhaps we haven't focused on too much, but is really quite interesting part of this story, is just, and it was mentioned, I think, by Andy briefly, is the blueness of the early light and the fact that we were seeing even really quite bright ultraviolet light once we started to observe the transient source, the explosion. And the question is that's really quite a surprise, and the origin of that is not too clear still. And I think if we'd been able to fill in those first 12 hours, that might have become clearer. It's hard to say, of course, without actually having it, but that would have certainly given us some extra clues as to whether there's multiple components here, whether there's somehow other sources of light beyond just the kilonova that we've been describing that might be also in play.
Jim, can I circle back for a second to the galaxy? So as you can see from the Hubble images, the galaxy itself, you're asking how bright it looks, but in its actual intrinsic brightness, it is very similar to our own Milky Way galaxy. The main difference being that it's an elliptical galaxy, not a spiral galaxy, and so the stars in that galaxy are much older than the stars in our own Milky Way. And that's one of the ways that we can tell the age of the system, how long it took the two neutron stars to merge.
Yeah, so I want to just point out one additional thing. We might have missed a few hours because the sun was up, but if this event had been 9 days later, it would have been after LIGO went down for its upgrades, and if it had been a month later, the source would have been just almost directly behind the sun, and so I think we were pretty fortunate. I had a question I saw over here. Did I? Nope.
Well, while we're figuring that out, I would say that for the brightness of the source, it was about 17th magnitude, if you know what that means. But it basically means that amateurs could have caught it with their telescopes had this been a big public alert like the future ones will be. So, this could be exciting for just anybody with a telescope.
As Brian said, a 16-inch could do it. Yes, over here.
Hi, Sarah Kaplan from the Washington Post. Since these neutron star collisions are visible by traditional telescopes, is it possible that past ones have been observed, and are you guys going to be going back through old data and trying to detect other observations?
Laura?
I can take that one, yes. We have never seen a binary neutron star in our data before, definitely not one of this magnitude. So this was possible because in the current run, we have higher sensitivity than before. These events are pretty rare. I believe in the previous panel, Vicky mentioned that this type of events happen, once per million year in a galaxy. So we were sensitive to fewer galaxies in the past. And so this is the first one of its kind in our data. But we are looking forward to taking data at bigger sensitivity, and so seeing even more galaxies and more of these events in the future.
Ryan, did you want to say something?
So for the light, there are a number of supernova searches that might have been able to find this, but it turns out that because this object was relatively faint and faded so quickly, that the number of potential galaxies where we could have seen this in was rather small. It had to be a very nearby event, and it actually had to have occurred in the last few years when supernova searches were like what Dave has, something where it's essentially every day. So we've looked through all of the previous data, and we haven't seen anything even close to like this.
So if I could just add one thing, our one-day cadence supernova search, we did calculate roughly how long it would take if we ran our survey, how long it would take to find one of these, and it's something like 15 years. Yep.
Okay. Do I have a question over here, or does... Okay, LJ has the web questions.
Okay, this is from Jesse Emsbach from Live Science. So this confirms that heavy elements are made in an R process in neutron star mergers. Does it fully account for the observed abundance? And then he has a follow-up. Older theory said heavy elements came from supernovas. Is that now excluded by this observation?
So who would like to take that? Ido, you saw your hand.
Sure. So of course we have, in this particular case, one event, and we have a measurement of how much material was produced of these heavy elements, 16,000 times the mass of the Earth. We don't know if this is a typical event or if the other ones that we will see in the future will produce more or less of this material. But I think as an initial calculation based on our understanding of how often this happens and the amount of material in this one event, it seems that we can account for all the heavy elements beyond iron and nickel in this fashion. I want to stress that it doesn't change our view that supernova explosions produce the heavy elements up to iron and nickel. But I think that with this neutron star binary channel, we can explain the heavier elements without having to rely on supernova explosions to produce the heaviest elements.
Next web question.
Great. Another question. Hello and congratulations from Brazil. Is it possible, knowing the amount of gold or platinum that can be created in neutron star collision?
Marcelli, you're home. You want to answer?
Yes. So yes, it is possible to know. We actually have that's one of the results that has been published. I think that Ido has the numbers of what was the amount of total heavy elements, and so that is one of the major aspects of this, is being able to tell that.
This is from Sarah Bosman. We heard earlier that gold and platinum were formed in the merger. Are those elements formed preferentially in these events as opposed to normal supernova? And why?
Yeah, I think that that seems to be a question that's coming up often. The supernova processes, they are capable of producing heavy elements. It's just not efficient enough to produce it in the amounts that we observe. So to produce the amount of those elements that we observe on Earth, we need a mechanism that is more efficient. And these neutron star mergers are that mechanism.
I could add another point that maybe addresses some of these questions, and it relates to the fact that I mentioned that the theory of the mergers is very complicated, and how the material's ripped out and what it does is complicated. But one aspect which seems to be pretty well tied down is how the synthesis of the elements takes place if you make the right conditions. And so that's something which seems to be well understood, and we already knew that even before we made these observations, that the relative abundances of different chemical elements seems to be well explained by existing nuclear theory. And so in that sense, if we know the conditions are right, then it should happen, and that, I think, is the main significance of what we found.
Yeah, well, I want to point out, I think in the first panel, someone showed a spectrum that had these very broad lines. And remember, this material is moving out at a substantial fraction of the speed of light. So because of the Doppler effect, that really spreads out the lines and makes sort of spectral analysis of the quantities of each metal rather more difficult.
Another question from WHBF TV. The question is, to what extent does this answer the predictions made by Einstein, and was there anything which he did not predict, such as the lack of X-rays visible early on?
That sounds like Dr. Trojka can answer that one.
Yes, definitely. I don't think Einstein really worked on electromagnetic radiation that much, so he was not working on prediction of X-ray and radio. So this is something Einstein did not predict, but someone else predicted, as we said before. We knew that this was a possibility, that X-ray and radio signal could appear at a later time. About the prediction of Einstein, I think maybe a LIGO colleague would be more appropriate. I don't know if Laura wants to.
Yeah, sure. So the kind of things that we test in LIGO data are, and we can say something more about now, is do photons and gravitational wave travel at the same speed? And that's something that we had the first evidence for this time around. We have so far not been able to prove Einstein wrong at any point with anything related to gravitational waves, but we're going to keep pursuing this as more, keep trying. As we look for more sources, we are expecting to find more events, not only binary neutron stars, but also binary black holes that are coming from farther away. Careful studies of the gravitational waveform can tell us about again, dispersion relations in the propagation of gravitational waves. These are all things that we keep testing, and we'll be doing more as time goes by, more events are found.
If I may add, there's also cosmology. That is one of the big questions we are trying to answer, is whether or not Einstein's cosmological constant is actually responsible for the accelerated rate of expansion of the universe. And gravitational waves are providing us already a new way of determining that, and it will get better and better as we accumulate more events. So at least for me, the most exciting part of this is that this is the first event, but it's not the last. We will see many more, and that will become way more interesting.
So I wanted to ask Dr. Sand a question, because as you say, there will be many more, and we heard about that earlier as LIGO and Virgo are more sensitive. So you used a 16-inch telescope. Is there room in this game for amateurs, people with 16-inch, 24-inch, 32-inch telescopes in their backyards, and how would they get involved?
I think there definitely is room. You know, our observatory is robotic, and everything about it is sort of automated. But if you're an amateur observer and the LIGO alerts start becoming public, and especially if the events appear pretty close, you know, within 100 megaparsecs or so, those events may be rare, but hey, why not? Go for it. You too can participate in this great adventure.
Can I also add?
Yeah.
Beyond amateur astronomers, which all could potentially do this, essentially every college and university in the United States has a telescope capable of making these observations. So if there's an event like this, I don't think we are going to be the ones making the discovery anymore. It'll be somebody, in this case, it would have been probably somebody in Africa with a relatively small telescope. And so we're not going to be out of a job yet, but you know, I think there really is a role for amateurs in this.
Okay.
I just want to make sure, are there any journalists who have questions? I have a couple more questions. Okay. Now that you know there is a black hole at the precise location, can you do something with it? And this comes from Swinburne University.
What can you do with a black hole?
We can add it to the census of the black holes that we know about. And I think, as was mentioned in the previous panel, it's actually an interesting black hole, if that's what it is. It's the lightest one that we know about. And so I think this will teach us something new about the range of properties of black holes.
Okay, kind of similar. What is the product of this collision? Which band of wave is most bright in this event? And what can we learn from different frequencies observations?
So I'm going to pass that one to Dr. Corsi, because I was going to ask you a question about the gift that keeps on giving. So this is your chance.
So for what concerns the radio, actually, we don't quite know yet how bright it's going to get. So it's getting brighter. And depending on where it will peak and how long it will take to do that, we're going to learn several different things. So I would say in the radio, at least, the story and the answer to that is still unfolding. That's why we're going to keep monitoring this event for months, possibly even years to come.
And don't forget the gravitational waves that will continue to be brighter.
Absolutely, yes.
Another question. How would the formation of gold, platinum, and other heavy metals be exported so we can have access to them on Earth?
Well,
yeah,
go ahead, Andy.
Well, I don't think we'll be getting access anytime soon, but you know, our descendants, and you know, probably we're going to have some sentient robot descendants in the future. Maybe they can figure this stuff out. You know, Carl Sagan likes to say we are star stuff, but our robot overlords will say we are kilonova stuff because they're made out of this heavy stuff.
Few from the world students. Okay, another. This is coming from space.com from Calla Cofield. With the dawn of this new era of astronomy, what practical changes can all of these observations expect? Will gravitational wave events become a frequent thief of EM astronomy time? Will we see students majoring in multi-messenger astronomy?
They didn't steal anything. No, they gave us a great gift. So, I mean, everybody up here should be incredibly thankful to the gravitational wave astronomers. This was an amazing gift. We learned a lot about the universe.
think our anticipation is that there will be many more events in the future, as we heard from our LIGO colleagues, and which is both extremely rewarding to think about and terrifying, given all the effort that has gone into this one event. So I think there will be more people joining this party, and a lot of new students, I think, will be excited in this new field.
Yeah, so one of the things we've seen historically is when we used to get a gamma ray burst every once in a while, lots of telescopes would follow up on it. And when you started getting 2 a day, you had to pick and choose a little bit more about saying, what specific thing am I going to learn from this object? And we see the gravitational wave astronomy moving on the same path, where I'm committing these folks over here, right, to getting their upgrade to better. But when you get to events once a week or every couple of weeks, then I think we're going to have to do a little bit more strategizing about how to best follow them up.
Very rich time, data rich. And it will also enable, I think, a diverse ecosystem of different types of telescopes, different types of observatories. There is room for small robotic telescopes. There is also room for large wide-field cameras to try to search for the events that happen at 10 times the distance. We just heard earlier that the next round of these observations will be able to see events all the way out to a volume 8 times larger than it is right now. That means further away objects that may be faint, and there will be room there for other types of telescopes to observe with different strategies. So there is certainly, for anyone who is even considering perhaps launching a career in this field, there is certainly a lot to be done, and it will be a great adventure.
Okay, we've got time for one more question in the room, if there is one. So let's take in front here.
David Ernstein from American Physical Society. I still don't quite understand what it was that was special about having LIGO involved, because in terms of seeing all of these other wavelengths. There have been many observations of gamma ray bursts and optical telescopes turning towards those. Why haven't you seen all of these whole range of wavelengths and events in previous gamma ray bursts that have been observed in the past, even without the gravitational wave signal? Thank you.
Laura?
If I can comment on this one. So we heard from Julie McHenry earlier in the first panel. This GRB would probably not have been followed up at the same level of attention that it has. It was not particularly bright. It was not a special GRB. So the fact that we had a gravitational wave signal that's the gravitational wave combined with the GRB signature was really something worth following up on. So that was what triggered the whole attention. And then now,
Another key aspect. Another key aspect is that the gravitational wave signal can tell us that this is a neutron-star merger, that is the mechanism. And that, in turn, means that a number of the predictions that we all had for how this would look like in the different wavelengths, we can out-test all of them at the same time. We had seen other gamma ray bursts before, but we didn't have somebody to tell us this one is a neutron-star merger. Pay attention to it.
Okay. So other these other gamma ray bursts had an afterglow that was really this, gamma rays, X-rays, all the way down to the optical. This one, we didn't have that, so we could see the kilonova underneath. That kilonova has been masked in all previous, with a possible exception that people have claimed before. But this time we could really see the underlying kilonova.
Okay, I'm going to take one more comment from Eleonora, and then I think we're going to have to end.
To answer your question, all the other gamma bursts that we saw with Swift were different because this jet was pointing directly toward us, and it was outshining everything else. So we didn't see any of this stuff. There was a kilonova, but it was outshined by the light of the gamma ray burst glow. That said, I think we saw some of these events before, in Fermi and in Swift for sure. In 13 years of mission, 9 years of Fermi mission, there are definitely some of these events in our database. But the thing is, The X-ray light took 9 days to show off. So in previous case, we just did not realize what was going on. So we saw them before, but we just did not realize they were nearby neutron star mergers because we did not have LIGO to tell us this information.
Okay, I think, Susan, we're done, right? Okay, I'd like to thank the panelists, thank all of you for all of your attention, and pay attention to all of the papers and exciting results you'll be hearing about from this for a while to come. Thank you.
We back?
Yeah, just hold it on that until Anna.
Okay, you ready? Okay, we're back. Hi, everyone.
Okay, welcome back. So we'll be here for the next, sorry. The press conference ended a little sooner than I thought, so I had to run that. Okay, so we're back answering your questions. We're going to be around for the next 30 minutes or until questions run out. And our first one up is from Eugene M. Do gravitational waves have different frequencies? Like electric and magnetic waves, is there gravitational spectrum? If so, what information can we get using gravitational spectroscopy? Okay, so this is a question.
It's a good question. I'll let you catch your breath again.
Go
It's a good question for especially talking about space-based detectors. So we mentioned earlier, yes, gravitational waves are emitted across all frequencies. For an astrophysical system, the frequency of gravitational waves that it emits kind of depends on the period of that system. So if it's a slow-moving system, then it emits very low-frequency waves. And if it's a fast-moving system, like the neutron star system we saw announced today, then it's higher frequencies, kind of in the kilohertz. And so I talked earlier about the aim of taking a gravitational wave detector into space is to be able to see these very, very low-frequency gravitational waves.
Can we throw up to the sensitivity curve again, guys? Number 201.
Maybe I just draw it.
There we go.
So you see in this,
you want to show it down here?
in the middle band here, this blue band is the space-based gravitational wave detectors, and they're in a frequency range of about 1 millihertz. So these are things that are orbiting each other once every kind of 20 minutes. And in these regions, then we're looking at really, really massive systems that are slower moving. So we're looking at
EMRIs, extreme mass racing spirals. So that's what I spend a lot of time doing.
That's right.
Can we throw up a picture of our EMRI, which is, wait, where are we? Our EMRI is number 111. Right, so when you go into that LISA spectrum, what you're going to see in space, one of the main signals is EMRI. So that's when you have a supermassive black hole and maybe a smaller black hole gets kind of nudged into it. The supermassive black holes we think actually exist in the center of our galaxies. We're pretty confident on that because people are actually spending a lot of time and energy tracking the one in the center of our galaxy. And it's these very cool pictures where you can see all these stars whipping around something that we can't see. But because by looking at all the movement of the stars around it, you can say this is a black hole. But can we throw up that picture? 111? Oh, it's not showing up? Okay. Well, it's only an artist's impressions. They're actually very important. But basically, you can have like a huge black hole, and then a little black hole kind of gets stuck in. And these are really interesting because the little guy kind of holds his own against the strength of the big one, which means he really does a slow in spiral in. So remember those ones that we were looking at, and they were like, it was like fractions of a second. Well, these guys, we're going to track them for months. That's how long it takes for the merger to happen. And that whole time, so for months we'll be tracking the same. And we can track loads of them at different times as well. And if we track loads of them at different times, then we can get information like on the Hubble constant and stuff like that, can't we?
We can.
Yeah.
We can. Yeah.
So there's like just all this. There it is. Okay, so this is one of the NASA images. So you can see you have a little black hole formed with a big black hole, and we do think this is the kind of thing that would happen quite a lot in the center of our galaxies, because our galaxies there's so much chaos. You think it'd be quite easy for something just getting nudged in, and then start this awesome spiral that will last for months, and hopefully we'll see loads of those. And then if we can we throw up the last image, the Susanna image? And then, like we were saying before, if you, number 203, if you, 203?
We like this curve a lot.
We do like this curve. But basically, so this was the one I was talking about earlier. So what's very, very nice about this is that, you know, had LISA been operational before, we could have actually, LISA would have seen that first detection first, and then it would slowly come into the, so this is in the LISA band, then it would slowly come into the LIGO band and then plummet, and this is where LIGO picked up the signal. And like by following that same guide, there's so much more information, so much more physical constraints we can put on everything that we're doing. So
you can
like,
say to within a few seconds, right, when you expect this system to merge in the
you can really go, labs, this
LIGO
day, this time, this is when you have to be paying attention. And then the physics, the information you get from that is so much more. So like when we start doing multi-frequencies, things are really going to start getting interesting. Sorry, I kind of ran away with that question.
Yeah, no. And Dunshu Wu is asking us, so when are these satellites planned to launch?
Right, yes,
so this, we're aiming to do this in the 2030s is when LISA will be finished. So we're just starting to build that satellite now.
Yes. So LISA is this three spaceship configuration with the 3 interferometers that the European Space Agency is launching. But NASA is also a minor partner in that as well. And then a lot of European countries and countries all over the world are putting money and energy resources into that. That's going to be 2034. It's going to be exciting. Have to wait a while.
We'll be here for a while.
Okay.
Still young.
Yeah, still got time. Okay, so Francesca Maria wants to ask, from the 2-second delay, what is your preliminary opinion to the model of the G or B emission? What do you expect about the post-merger phase of this event? Okay, so Kendall, I think this could be one for you.
Yeah, so what we can determine from the 2-second delay is that there's actually two populations of gamma ray bursts that we know about. And so the first one is for gamma ray emission, which happens roughly 2 seconds after some cataclysmic event. And then we also would expect potentially emission from, let's say, a stellar collapse or like a massive star collapsing on itself, and that would be what's called a long gamma ray burst. And so these are very distinct formation channels. So because we've seen it within 2 seconds, we know, well, we can sort of pinpoint to this idea of it being a short duration gamma ray burst. And so what does that mean for the emission? Well, it's an interesting case because we expect to see an X-ray emission afterwards with potentially a short duration gamma ray burst afterglow, which happens when the matter starts bumping into each other and exciting each other and heating up. But we didn't see something like that. So there's a lot of interesting ideas about why that is. One of the ideas is that we're actually looking at the gamma ray burst right on the edge of the axis, or maybe that is some sort of bubble happening.
I'll just draw a little picture here. So,
but we don't really know what. That's right.
There's the gamma. And the afterglow is a bit on either side. And then the kilonova,
right.
is all the crop
so,
that we saw comes from everywhere.
That's right. So what we ended up seeing was this, what happens when the jet starts to slow down. So things are, all the particles are kind of moving and losing energy and losing their momentum. So the jet starts to spread out a bit. And it's when the jet starts to spread out and intermix with all the materials surrounding the star that we can see this thermal radiation, which is called the kilonova itself. And so what happened under those layers, so what happened to the neutron star itself, the binary system, we don't know yet. You know, a variety of different scenarios exist, but yeah.
Is there any way of telling what actually happened next? I mean, can we get any radiation off this remnant at all? I know it's not emitting any more gravitational waves, but is there anything we can see with the EM radiation?
Yeah, so with the EM radiation, we can expect to evolve across the electromagnetic spectrum. So we can start to see initially within, you know, the first few seconds, we could see gamma radiation. And then as it moves through to the ultraviolet and into the optical, and then down into the X-rays and the radio. And so we can see this evolving over different time scales and you know, and try to piece all these.
Can we tell if it's a black hole or not?
No.
No, okay.
Well, what we can see is that we just have this material that's being blown off, and we see the material that's being blown off and interacting with the surrounding medium. So that's what we observe.
Okay, cool. Thank you, Kendall. Okay, so next question is, how can we predict the next gravitational wave? Well, I guess, well, actually what I was saying before, if we have a space-based detector, or when we have a space-based detector, that will definitely be able to tell the ground-based detectors, you know, here, something's coming in like about 2 years. But also, I mean, like, there is like binary pulsars that we know of. When we say pulsars, it's a neutron star that we can see because its axis is kind of turned towards us, and we see this beaming light that it's emitting. So they're kind of considered like lighthouses or sirens of the universe. But basically, we can see these guys, and sorry, I had to, yeah. So there is one in our, the Hus-Taylor binary pulsar we can actually see, and we do know that's going to emerge and emit gravitational waves, but it's going to be in 300 million years.
Yes,
so
not soon. Not soon.
A little far out, but I mean, I guess technically, I mean, if we could see one that's, you know, closer electromagnetically, maybe that could feed into the gravitational wave. Would that be right, Kendall? Can electromag tell gravitational waves? Inform the gravitational wave community?
Yeah, so we can have a gamma ray burst go off, and it can be really bright, and we can say, oh, we expect it to be close by. Let's go back and look at the data and see if there's anything we missed. So we can do it that way as well.
Cool, thank you. Okay, so our next question is from Fantasy Star OST. Can you get killed by a gravitational wave if you're too close to the source? Well, technically, if a very extreme gravitational wave is going to go through you, I mean, yeah, it's going to stretch and pull you. And also, if it's like one of these guys that we're seeing with the LIGO band with really strong frequency, I mean, you know, if I was stretched by a centimeter about 100 times a second, a kilohertz frequency, I'm sure my body wouldn't be happy about it. But I guess you'd probably be more worried about why you're doing so close to gravitational waves.
If I were close to two merging neutron stars, I wouldn't be worried about the gravitational waves. I'd be worried about the gamma ray burst and the explosion that happened after.
Everything else. Yeah, and same with black holes. You do not want to be that close to a black hole merger. So basically, it wouldn't be a good situation no matter what way you look at it. Okay, so Dawes Ganazers, how do you calibrate the detector if you don't know when there are no gravitational waves? Okay, Ryan, I guess this is one which would be for you.
Yeah, so that's a really good question. Is you get some sort of readout of your interferometer, but how do you know what that means? You know, how do you know what that corresponds to in amplitude of gravitational waves? So one thing we do is we take another laser actually and point it at the back of one of these test masses, N test masses, and we shoot laser light, modulated laser light, at these test masses at particular frequencies to actually move the test mass. So at very specific frequencies, we're moving the test mass. And because we know how much we're moving the test mass, because we know how much power we're putting into these beams, and we're just using conservation of momentum, when those signals show up in our dark port, we can say, okay, well, this corresponds to this much movement, and that's what we use to calibrate our detectors.
Okay, so we're pretty sure what we're doing then.
Yeah.
We know what we're doing. Okay, Philip Johns, which are the consequences of this discovery? What do we know now that we didn't know before? Okay, I guess I'll throw this back up to Ken.
I think really anybody could take this question. So
okay, well, Ryan, you can have a shout out.
What do we know that we didn't know before? Well, so now we know that the first detection was important because it told us that what we're doing makes sense. What we're doing is going to be able to do gravitational wave astronomy. This event is important because it tells us that we can interface with the EM community to probe these astrophysical events in gravitational wave spectra as well as EM spectra and learn more about them.
And hopefully in the future we'll have a neutrino detection to also complement.
Right.
That would be really cool, particle EM and gravitational.
Right, so this is the dawn of sort of this pairing of the two kinds of communities, the EM community and the gravitational wave community.
It's easy to get lost in the science, isn't it, but how hard it is to organize this and how many people are involved on this, on this day when this announcement goes off. There's a huge amount of activity. I'm not in the LIGO collaboration, but for you guys who are, it's like a swarm of emails and just everyone flying around.
And I'm sure the EM guys are also having the
same
there's
hundreds and hundreds of scientists all working on this and going into overdrive when these announcements come in.
Okay, so yeah, and I guess as well there was a bit of assurance about the whole kilonova. I think there'd only been one possible detection of a kilonova. So that's a huge, like telling, you know, no, we know that these models of neutron stars have got things right, that there is this thing called a kilonova coming out. Okay, so our next question is from Ordrin Schwartzman. What does the blind spot for these detectors mean? Okay, so I guess we can show a picture of the sky map, maybe. So blind spots can happen. Remember when should I draw the?
You can draw it. So, yeah. So if you have your L-shaped detector like LIGO.
Right.
And so if you have the wave coming into the page, then you're stretching and compressing these arms, right? But if your wave was coming in this direction, then I guess you'd be stretching and compressing the arms at the same time together, and that's not a sensitive mode for our.
And this is what we call the antenna pattern. So
exactly.
So here when you see here, we're saying like from what directions the antennas are actually most sensitive. And the fact that actually Virgo didn't have as strong a signal actually also gave a lot of information on the detection, because then you know it's in where it doesn't have very strong signals. So these really help with the direction as well, really understanding your detector and knowing where it's sensitive and where it's not.
The more detectors you have, obviously, as well, this fills in these gaps, right?
Yeah,
so
and it can really give you more information, because remember, like you're to find those where they come from. I mean, normally it's because it hits one detector first and the other. So, like if we had the two like American ones detectors, okay, if it comes from this direction here, obviously it hits this guy first, then the speed of light will hit this guy, and they're like, okay, so it's come from here. But you know, there's other angles that could come from have that same delay, and that's why when you first see these sky maps for the first few detections, they were like, oh, it's over here somewhere. And now the Virgo is in the game. They're really like, okay, no, it's right here and this little bit here. So that third detector is really coming in, and the fact that actually using blind spots to help actually narrow down this where in the sky it happened is very cool. Okay, so our next question: did you make a measurement of the Hubble constant? Okay, do you want to take this?
So, so we did, or LIGO did indeed make a measure of the Hubble constant. So the Hubble constant tells you basically how fast the universe is accelerating. So all the galaxies that we see around us, and this was Hubble's big discovery, are moving away from us.
Discovery.
Yeah.
We didn't know that the universe was expanding. Now we do.
And the way we measure this, so we look at the galaxies, and we look at the red or the blue shift of the radiation coming from those galaxies, and that tells us how fast those are moving away or towards us. And the great thing, and then we also need to know not just how fast they're moving away, but how far away they are. So traditionally we do this by looking for what's called supernova 1A, and we can look at those. That's a supernova where a white dwarf explodes, and we think that they emit light when a supernova like that goes off. We think that they emit light in a standard way, and so if we measure how bright that is, we can work out basically how far away it is, because all supernova 1A look the same. Okay. The amazing thing with the gravitational waves is we get the distance to the object for free out of the gravitational wave signal. So what you usually do is you plot a graph of distance against redshift, and you get something like a straight line that tells you how fast the universe is accelerating. And this is interesting to us because we have a couple of different experiments, not gravitational wave experiments, that are trying to measure the Hubble constant, and they have two values. They've come up with two values that disagree. So another independent way of measuring this Hubble constant is really good. So for now, we only have one data point. So our estimates with gravitational waves are pretty uncertain, and it covers both sides of the agreed measurements.
The gravitational wave community is saying both of you guys are still looking.
Yeah, we agree with both of you.
Okay.
But we're not accurate enough yet.
Okay, so we did make a measurement, but it's not accurate enough yet to actually determine which of the other two experiments, I guess, is zoning in on the right answer. Okay, so our next question is Rebel Yell. How can all the sounds and vibrations here on Earth be prevented from interfering with your sensitive equipment? Okay, Ryan, I guess this is another one for you because you're our...
Yeah, so we talked about this a little bit in the first Q&A, but so our test masses, which is what we're measuring the differential displacement of, are suspended on pendulums, a series of pendulums, which means when their supports are sitting on the ground that's moving, the pendulums sort of filter out this motion. This entire experiment is done in vacuum, and the apparatus that the experiment sits on are also isolated.
And I guess
so
you have
that's
a real understanding of all the other noise sources. So
right.
you
Yeah,
can move
noise characterization is incredibly important for an experiment like LIGO. But so we have to do things like suspensions, but people who go to space then don't have to worry about these kinds of things, right?
But we have to worry about other things like cosmic rays that you don't get on Earth, and
And also, wasn't there this thing with, I know for the Lisa Pathfinder, there was a lot of a thing about how to release a mass without putting any force on it whatsoever.
That's right. So
you're in space, so if you push anything just the slightest bit, it's just going to keep going. So they had to very carefully release the mass.
That's right. That's pretty difficult. That's a difficult job. So yeah, like you say, in LIGO, these things are hanging from a pendulum to isolate them from the ground. In space, you don't have to hang them. You just let them go free. Yeah. But
how do you let go
exactly.
Of
the thing that you're trying to let go of is 2 kilograms. Well, not that big, but 2 kilos, and you need to hold that tight as you launch it, right? So when you launch it, you need to hold it with something like 1,000 newtons of force.
Yeah, launches there's a lot
because
of
the whole rocket is shaking, but then when you get it into space, you want to let it go with extremely gently so it doesn't crash into the sides of your instrument. Yeah. And that's one of the big engineering challenges
different
that we faced.
Problems and different solutions, I guess. Okay, so our next question is from John Snelling. What happens if the telescopes are busy looking at other targets? Are there any telescopes that only look for gravitational wave events? So I believe there are. When you guys want to comment on there is a telescope dedicated, I think, for gravitational waves by LIGO.
Yeah, to my understanding, yes.
Does Kendall know more?
Kendall, do you know more about the LIGO telescope?
Yeah, so what happens when the telescopes are busy looking at other targets? So there's this idea that the instrument, the operators of the telescopes themselves will provide what's called the target of opportunity. So they have some understanding with the LIGO team, and they say, okay, a trigger has gone off, and then they will make every available effort to then slew their telescopes over to the spot that was identified, and either they will start to identify a tiling pattern, so to speak, over the sky map itself, or they have some sort of coordinates and then slew to those coordinates themselves. Now, in terms of telescopes that are dedicated towards gravitational wave follow-up itself, there's actually 2 instruments coming online that are currently in operation. There's possibly some more, but 2 of the one is called the GO2, is the Gravitational Wave Observatory, it's GO2. So that one's actually in development out in the Canary Islands, and then there's also what's called the Black Gem telescope. And so these are 2 wide field instruments, and they're built for rapid follow-up, dedicated towards gravitational wave events.
And then I guess this picture coming up beside me, Kendall, I think you can see it. What we're showing here, that's the that's the Kilonova, is it, or was it the remnant? Can you?
This is a Hubble Space Telescope image.
It looks like it says it's Kendall. It's not Kendall. Oh. So I guess it's very important for all these telescopes as well to go quickly, because this guy disappeared quite fast, didn't he?
Right.
This is a Hubble Space Telescope image. I don't know how long the optical lasted.
So in this case, what we would want is, there's always going to be some trade-off between how fast you can get on it and then how much time you have to stay on the target. So ideally, you can as quickly as possible, and you can image for as long as possible. And so with the goal of being on the target as quickly as possible.
Right, okay, so here you can see how it actually faded. So this is why it's so important to get those telescopes there very quickly and have that really nice communication with the EM community, because if we guys weren't working together, like all this physics would have been lost.
So I want to say that that just because, so there's the option that while you're in the optical, you can see the transient like this in the visible, but if you don't get on the target quickly enough, it's okay, because the system begins to evolve. So you can now bring in other instruments like the X-ray instruments and look for the X-ray observations, or you can follow up at a later time, days to weeks later, and look for it in the radio. And so there's a lot of different mechanisms for this particular type of source that even if you don't get on the target, you can still tell a lot of history, but you can maximize your signs by getting there as quickly as possible.
Cool. Thank you, Kendall. Okay, so our next question is from the mad philosopher. Please tell me what causes gravity. Okay, so we'll do a quick gravity 101, I guess. Everybody told me on no circumstances am I to write an equation on this board, but I'm going to write an equation on this board. For every character, apparently, we're going to use 100 views. So, okay, so basically, if you think of Newton, where it all started, okay? Basically, I'm just saying this is a force. And what a force is like if you move a mass, you change its velocity, like I just changed Peter's there, I applied a force. Newton notices the apple, he's like, okay, something caused, it's got a mass, it changed velocity, it has to be a force. So how do you calculate it? After lots of observations, you figure out, okay, well, the force, it's, you know, the bigger the masses, so I'm not very big, he's not, well, there's no gravitational thing here. But like, if you had an apple falling, you see it because the Earth is so big, but you don't see us like moving towards each other because our masses are quite small relative to that. I mean, so you think of magnets, I mean, there's strong magnets, there's weak magnets, and when you put them together, you know, the strong magnet can overpower. And then the R squared is just telling you, hey, the closer these masses are, the stronger they're going to feel each other's presence. So again, if you think of the magnets, when you bring them close, it was always, you know, as a kid, really hard to hold them as close, but, you know, without the two magnets colliding. But if you held them out here, it's like, you know, they didn't know the other one was there. And that's what this R squared is telling you, that when planets come close to each other, then they start feeling each other's mass. But if they're far away, they're not aware of each other's presence. And what this G guy is here, he's the gravitational constant. And that's just showing telling you that the force is really, 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 really weak. Which is again why, even though I have a mass and Peter has a mass, we're not slowly being pulled towards each other, because this guy has a 10 to the minus 11. So if you multiply our masses, divide by the 1 meter, and then move the number by 11 decimal points, that's how strong the force is. So that's what caused gravity. It's basically mass, and the mass being close enough that it can feel each other. Now, as we know, Newton was the old school. We have, you know, Einstein then took over, but I won't get too much into that, because Einstein's equations beautifully cancel down to Newton's on Earth. So all the complicated stuff just beautifully falls out, and you're still left with this guy. So that's what causes gravity, mass. Okay, so our next question, I hope everyone likes my equation. Oddly Dangerfield Music wants to ask, what practical applications does this discovery have? Okay, guys, who wants to take that one?
Well, I guess obviously the reason we do this in the first place is to learn about the universe, right? But in doing it, we developed some pretty amazing technologies. This is, you know, one of the most challenging measurements ever made, and just the problems we have to solve in doing that can generate applications for industry and other things. Sometimes we don't know exactly right now what those applications are going to be.
Right, and I'd like to make a very good point on that, because when you think back to 1915, when Einstein came up with his beautiful theory, I mean, when everyone's there going, what are the applications for this? I'm sure Einstein was like, well, you know, now we know how the planets are going to orbit properly. But what happened then, which Einstein and no one at that time knew, was you fast forward to 60, 70 years later, and the US decided to develop what now is called GPS, Global Positioning System. And it didn't work at the start. And nobody knew why until people said, you know, because of gravity, clocks tick differently when you go up in height. And once they took that into consideration, there's this lovely curve, I don't think I put it on the thing, where you actually see when they decided to take gravity in, and everything just goes beautifully. So practical and industrial applications right now, we don't know, but who knows in the future what all this physics will mean. But for now, I guess we're just doing beautiful astrophysics.
That's right.
And cosmology. So for now, it's just for the science lovers, but who knows down the line what any of this can tell us, because the more information you get, you don't know where it's going to lead you. Okay, so our next question is, do very mass objects, galaxy clusters, dark matter patches affect gravity wave propagation with gravitational waves? So, well, yeah, they do. So one of the issues that we have with things that we observe when we're observing all the world, the universe around us, is that actually it behaves like there is more matter in it than we actually see. And this is why people actually start proposing dark matter, because, and they see it in all scales. You see it on a cosmological, so when we say cosmological, we mean like you're looking back into the Big Bang, like really long time ago. But also when you look at galaxies and everything, you know, you can see the gravity's curving, but then they look into the galaxy and they're like, but there's not, the light is curving much more extreme than the amount of mass that we know that's in there. So there's something else in there, and what is it? And same like the universe is expanding, you know, and it's expanding, that expansion accelerating. We don't, you know, to have that, there's this missing mass, and that's what we talk about dark matter. So these stuff does actually affect the gravity, and that's why they've actually even been proposed into existence, is because there's something not quite adding up there. Now, that's a huge thing. Like, people are really searching for dark matter, and it's a really exciting field, because when we solve that problem, it's going to be fantastic. So
not just dark matter, right? It's dark energy,
yeah,
which is
even bigger.
So we think we have some idea of where we can see dark matter in the universe. You know, it's acting gravitationally, but we don't see its light.
No.
Dark energy is something that supposedly takes up, you know, 75% of the mass of the universe, and we have got no idea what it is.
Yeah, I think, or maybe even more. But yeah,
it's causing the universe to accelerate apart at the moment, and we have no.
So the reason we even suggest that these things exist is actually from gravitational and electromagnetic observations, because they're not following the gravitational laws. Okay.
I mean, one of the things, we talked about gravitational lensing and things, and one of the things that affects how precisely we can measure these waveforms is actually the material in between us and the gravitational wave source. So if you have if you're looking at a gravitational wave source a long, long way away, and there's lots of stuff in between that you don't really know what's there, that kind of gives you a systematic uncertainty on what your gravitational waveform really looked like when it was being emitted.
Yeah. Okay, because if it comes across something like a black hole, that could actually whip it, you know, and strengthen it. You know, so the gravitational waves can be altered by other massive objects. I mean, they really have to be seriously curving space to have an effect, but it can happen. Okay, so our next question is from WOOKI33. Love the name. What specific fine-tuning of the LIGO instruments will take place over the course of this year? Okay, over the course of I guess you're shut down for your... Is this all top secret, or are you allowed to tell us what actually you guys are doing in the next year, and what kind of improvements we're going to see?
Yes. Well, so most things aren't super interesting to outsiders, I guess. A lot of the control loops in LIGO are you know, tuned. Sometimes even during observation runs. But so the improvements to LIGO in terms of most nearest to us to most far future would be increasing the power in the cavities, implementing squeezing, and...
But doesn't increasing power lead to its own problems?
I mean, how much power are we talking about is the other thing, because that's pretty impressive, right, for people who don't really deal with this every day.
Right, so
the amount of power circulating here.
The amount of power circulating in the cavities is on the order of kilowatts, which for...
They're perspective, what's a light bulb? 40?
Yeah, 40 watts, something on the order of that. So
thousands of light bulbs.
Thousands of light bulbs. But this is all also coherent light as well. So this is light that's concentrated into a laser beam. It's not diffuse like your light bulb or anything like that. So increasing the power circulating in the cavities, then implementing squeezing and also so another thing that is maybe not in the immediate future but on the near horizon would be things like gravitational gradient subtraction from the signal.
And I guess that just means those curves that we were showing earlier, where you had Virgo, Hanford, and Livingston, they're all going to drop.
Yeah.
And then we're going to just see more.
Right. The idea is the more sensitive our instrument is, the further out it can see, so that increases the volume of space that we can see sources from, which should increase the event rate.
Okay, thank you, Ryan. Okay, Alan Morgan, what units are the amplitudes measured in? Length, question mark. Well, again, it's unitless, right?
It's unitless.
It's
okay,
meter per meter.
That's right. It's change in length divided by length. It's a strain. Right, yeah.
So you're basically what you're measuring is the percent, like we said, a lot of time you hear people go, oh, it's a strain of 10 to the minus 22. And that's 10 to the minus 22 4 kilometers. So we're basically saying it really depends on the length of your instrument what you have to measure. So we have a 4 kilometer instrument, then 10 to the minus 22 means we have to do 10 to, well, because there's it's 4 kilometers, yeah, so 10 to the minus 18 meters is what they're measuring. But the actual amplitude is that over the 4 kilometers, so that's why it's dimensionless. But also then I guess for future ones, I mean, there are talk about going way more than 4 kilometers, because then you have to measure less. Well, not measure less, you don't have to be as accurate.
Yeah,
That's right.
there are also a lot of technical reasons for going with longer baseline.
Yeah, yeah.
It's not just that you can increase the displacement that you see, but things like thermal noise of the coatings are mitigated generally by having fewer reflections off these surfaces.
But I guess that's a lot further down the line, because
Yep.
that'd be
Yeah,
post
those
LIGO.
those are post LIGO. It's not simple to build, say, a 40-kilometer vacuum tube.
40 kilometers is long.
I mean, and then going to
and
space.
having a vacuum for 40 kilometers
That's
as
very,
well,
that'd be
right?
very expensive. That's a
gonna,
very long.
That's going to cost.
But going to space is the ultimate.
Is the ultimate
goal
vacuum
then, right?
as well.
Because you have all the space you need to make a huge detector, and LISA will be kind of 2.5 million kilometers between the spacecraft. Okay, so you're basically building a LIGO, which is 2.5 million kilometers along the arm.
So some good stuff going to happen in space as well. Okay, what is the minimum event that can produce gravitational waves? I guess any quadrupole would be the answer.
That's right. Any system, any gravitational system will emit gravitational waves as long as it has a quadrupole
well, I mean,
moment,
everything.
right?
Okay, yeah. So basically, what you need is a mass. It has to be accelerating and not to have spherical or cylindrical symmetry. And once you fulfill all those, it will emit gravitational waves. Now, so I mean, this is emitting gravitational waves, but you're never going to detect those because it's not very massive. So the bigger the object that's involved in all this accelerating and stuff, the stronger the waves are going to be, and hence that's why we can only detect them from these crazy violent situations that are happening in our universe. Okay, Wesley Hirsch, are we going to see a significant increase in the number of gravitational detectors across the world in the coming years? Or is 3 to 5 sufficient to provide the data we need? Well, we want there to be a significant increase in the number of gravitational wave detectors, but that all depends. I mean, for sure, LIGO India is going. Kagra, the Japanese one, that's coming online, I think, hopefully next year. That's huge because they went underground and they're using cryogenics to get rid of thermal noise. So that's really going to be new stuff going on there. And then LIGO India has taken some of the mirrors that they had here in America, and they're working with India Research Council there to get that up and running in the next few years as well. Future outline, I don't know, Kendall, was there anything about Australia coming in or out, or is there still talk about that?
Nope, it looks
not. Still don't know. Okay, and then obviously we have the space. But like I said, there are these plans for Cosmic Explorer, Einstein Telescope. So there are people have spent a lot of time planning what would be the next step, but it's all about how much this costs. I mean, you always have to science versus cost.
Yeah, this was a $1 billion project, LIGO. So
yeah,
these are expensive detectors to build. So
yeah, but super cool
over
results.
A long time. Over a long time.
$1 billion
over a long time.
Yeah, and I guess you have a lot of manpower going in as well, doing all the analysis and simulations and source modeling. So, but yeah, is it enough? Yeah, it is. But like anything, I mean, the more you have, the better science you're going to be able to do. But like, I mean, we're happy with one. We got the one detection. It's amazing. And from here, we hope everyone else is excited as we are, and we'll get more and more detectors online and do even better science. Okay, so next question. With Kung Fu, with effects seen across the entire EM spectrum, can we expect to see a lot more of these type of events at other locations, since we now have a signature for gravitational waves? Okay, so who would like to? Kendall, would this be something you want to talk about?
Yeah. So with these, so now that we've seen different types of effects across the EM spectra, we were lucky to have seen just this one. So now comes the fun part of just going out and using the gravitational wave detectors to let us know that there's something interesting out there that probably, hopefully, maybe we've never seen before. And that could also be really exciting, is starting to kind of look around the universe in a different way than we have in the past, to find new and exotic and interesting astrophysical objects.
Yeah.
And so we don't quite know what could be out there.
Right, so I guess if we saw something like a supernova, that would be something that we could see gravitationally and in electromagnetism. That also could be super interesting.
Right, and so we could see things like, with coincident neutrino emission. We could see maybe things called what are called the fast radio bursts. There's a gap in the literature of what we expect to be our astrophysical transients, or what we know about our astrophysical transients. And so there's this idea that there's this missing gap of what we know that we're looking for, and we fill it up. And so maybe the gravitational wave detectors can help us in that venture.
Cool. Thank you, Kendall. Okay, next question is Stephen, I apologize for pronouncing this wrong. Piatkowski, thank you. The laser beam actually reflects multiple times along the 4 kilometers, doesn't it? Yes, it does. Right.
Yeah, it does. So so what we could do is we could build a LIGO instrument with a beam splitter and 2 test masses, and just send those beams, hundreds of thousands of kilometers in one direction, and then recombine them. But that's pretty impractical for our purposes. We already have 4-kilometer long arms, and that's hard enough as it is. So what we do to effectively extend the arm length is we make these arm cavities resonant cavities. So light is bouncing back and forth and back and forth and back and forth, and increasing the times of that this light spends in the cavity, and effectively increasing the differential displacement of the test masses. So when we're talking about how sensitive we are to displacements, we have to factor in this 4-kilometer long arm, but we also have to consider that the light is taking many, many passes through this cavity.
Yeah. So yes, it does. Okay, so Lucifer LLS. How small can gravitational detectors be made if they were space-based? Well, they can be made very small, but I guess the idea is, like we said, they're more responsive if you have a longer.
That's right. So the idea is, if you're going into space, the idea is to make it big, right? Because you've got more room, and you're looking for.
You don't have to power it down to a vacuum.
That's
you don't
right.
have to evacuate all that air. You've already got space.
What you're looking for when you go to space, you're getting away from the low frequency noise and interference of the Earth, and you're trying to get the low frequency, very long wavelength gravitational waves from very massive systems. And so you want it to be big. If you're trying to measure big wavelengths, you want to measure with a big instrument. And you also have the advantage that we talked about trying to measure 10 to the minus 18 meters with LIGO. With a 2.5 million kilometer instrument, you're only trying to measure picometers. Okay.
Yeah, so you've got to remember that what you're measuring, the wavelength is, the wavelength of what you're trying to measure also has to be taken into consideration detector. That's why bigger detectors can see different frequencies, because frequency and wavelength are so closely related. But also I think Japan, there's been some talk in Japan about maybe doing a space-based mission to LIGO. It hasn't gone through all the stages, but I think they were looking at a space-based with shorter arms to try fill in that gap between ground and LISA. So you could see there was a space between the two. So there are other ideas out there. Whether they get funded or not is all just a whole other ballgame. But yeah, people have looked at that as well. But for us, you really get those beautiful emeries. There's extreme mass ratio in spirals. You want really big arms, and that's why LISA is going to be so good for that. Okay, so our next question is from I'm so sorry. Denalin DLC. Do these gravitational waves continue throughout the universe, or does it continue to ripple, bounce around? Okay, so basically they will continue to go. They will continue to go, and they don't really. They can be altered by other very strong gravitational fields, and even interact with each other, I guess. But there's not much that can actually deter them. So that's why they're so beautiful, because as long as it goes from there to here without hitting another black hole or something, we see this beautiful signal. Whereas, I mean, if you're getting like more low energy stuff like radio waves, I mean, a lot of things can interact with those. So we do have this very pristine signal. They can be altered or kind of almost beamed a little, but you need like black holes or something to actually affect them like that. So when they go through Earth, they just keep on going. Okay, so next question. How long is the wavelength of the detected signal? I actually don't know.
The frequency, right?
What's the frequency?
What does the frequency go up to? Around a few hundred
hertz,
I guess?
What was the frequency?
Yeah, so it sweeps through, this merger event sweeps through several different frequencies, right? And we see this event for something on the order of seconds.
This is what your sensitivity curve looks like usually, right? And the gravitational wave sources, as they merge and they get closer and they move faster and faster, someone's put a better plot on top of mine. Yeah, so they go.
So you're changing frequency.
They go up in frequency.
We might call that something like 10 hertz. That's where we can 10 to 30 hertz is maybe where we can start to see things, and then once we get to something like 3 kilohertz.
There's something I did put a thing on the screen. Okay, so there you go. So you can see the frequency. This is the frequency along
So
here.
they're really
so this
audio
is
bands.
So this is a time spectrogram, right? So this is Fourier transform along this y-axis, and then as it evolves through time. So you can really see this sort of uptick in the frequency of this event, right? It starts off as a low frequency, so we see something down by 40, 50, 60. It's sweeping up as it merges.
That's what he said.
And then also,
eventually disappearing.
Yeah, and that's what we were talking about, the space-based ones, because Lisa will be over here somewhere, and that's going to see a much lower frequency, which is different type of events. And then the pulsar timing array dudes, they're all the way over here, again higher, and that's why they're seeing different sources as well. So the idea is that each detector kind of has its own it kind of works in its own frequency band.
I guess the fun thing
the
with
neutron star binaries were here.
The fun thing with the LIGO is that these are audio frequencies, right? So if you play the gravitational wave signal as a noise, you can hear it.
Right, but you wouldn't actually hear that noise, would you?
Yeah,
you would. Okay.
Yeah.
Audio band.
It is audio band.
Okay.
Yeah, up to kilohertz. Yeah.
Okay. So our next question is Jos Schoonwater. I'm so sorry about my pronunciation. What is the difference in space-time shift between collisions from black holes and neutron stars?
Space-time shift. I'm not sure
what do they mean by space-time shift?
Gravitational wave emission, or the waveforms.
Oh, the waveforms. Oh, okay. Sorry. Someone had to give us a prod there. Okay, so the waveforms are going to be different. Well, I mean, they're both chirp signals because they're kind of equal mass binaries. And the chirp signal is what everyone's been seeing, which is, when you have this thing going, whoop, my very good audio version of that. And basically, but for gravitational waves, because they're much stronger gravity, you're going to, yes, thank you. So
time
one.
Frequency? No. Time and frequency.
It goes up. Anyway, but basically, it is a similar signal, but much stronger for black holes. But also because they were closer, you see a strong. So a black hole signal is stronger, but the neutron star merger was closer than the other one. So that does make it look a bit bigger, but still it was a neutron signal. And the black holes, I mean, actually, can we throw up that graph of the comparison to all of them?
I think actually,
it's number, because it really shows the difference. Oh, 105. Sorry, if you can just bear with us. Okay, here we are. So these are all the ones that we've actually detected. I keep saying we, but I'm on the collaboration ladder. I do source modeling. Okay, so here we are of all the ones that we've detected so far. Our LIGO and Virgo have detected, and what you can see is, look at this guy. The magnitude is just way bigger than what we have down here. But what we have down here goes on for way longer. Like these guys were, fractions of a second. This guy was up to 55 seconds, which is why you have that very beautiful noise signal ratio, because you have all this time to track the signal. But you can see that the black holes are much, much stronger, even though they were further away. I remember being closer makes it a stronger signal as well. So it's really like strength.
That's right. I think in terms of the actual gravitational waveforms themselves, I don't think it really matters whether it's a neutron star or a black hole, apart from the mass is different. Maybe as you get very, very close to the merger way over here, you start to learn something about how the neutron stars themselves are deforming, are being deformed by the merger process, and that can leave an imprint on the gravitational wave signal as well.
Okay. Thank you. Okay, so our next question is, Asaya Thomas, what happened to the galaxy this occurred in and the nearby planets? Kendall, all this exploding stuff, would that probably not a happy place to be when it goes off?
Yeah, no, if you're close to the source, yeah, it probably wouldn't be a good day.
Yeah, I've lost audio.
Okay, so I think when
Okay, sorry. Yeah, so I think that within the galaxy itself, so when the neutron stars, when they merge and the matter is ejected out, it might affect the galaxy locally, so perhaps even a large portion of the galaxy around it. However, if you have some nearby planets, for example, those, depending on mechanisms at play, if they could be heated with the material, they could be thrown out, things can be thrown out. There's this idea that even with the two neutron stars itself, it's such an energetic and quick moving process that one of the neutron stars in the binary can be shot even out of the system. So just a bunch of material and a bunch of energy is just going all over the place. And so, though, on the thing that the galaxy itself should be maintained, it'll just have some local disturbances.
Okay, but you definitely wouldn't want to be nearby.
No, you definitely would not want to be nearby, especially in the cone of the gamma ray jet. No.
Yeah.
So I mean, if this happened in our, if that beam of gamma rays was in our galaxy and nearby and pointed at Earth, is this a kind of a very bad day for Earth? Is this like mass extinction, or is this?
Yeah, this would be a very bad day for Earth, and I think even there was some explanations that an extinction could have happened because of some gamma ray event. Whether or not that's confirmed, but just the idea that it is a very destructive event.
Yeah, okay, thank you, Kendall. Okay, next question is from Wally Thompson. What is used for the reflective surfaces of the mirrors? Okay, Ryan, I'm going to throw this one to you.
Okay, so yeah, the test masses themselves are glass. They're fused silica. The reflective coatings are a series of silica tantalum layers, which use constructive and destructive interference to either be reflective or anti-reflective. So right now, a lot of research is going into constructing new coatings that are particularly quiet in terms of their sort of thermal properties. And they're because one of the noise sources in advanced LIGO is we have coatings on these mirrors, and all of these across this mirror, there's a bunch of atoms, and they're all thermalized, and they're all moving sort of randomly. And that is going to show up at some point in your detector output as movement of the test masses themselves, which you don't want to see. You don't want to see thermal noise on the coatings showing up in your gravitational wave signal. But for now, they're amorphous coatings. But there have been people looking into constructing crystalline coatings. It's a big topic of research right now.
Okay. Thank you. Okay, our next question, Aman Shrivastava. How can we be a part of gravitational wave detections in the future? Okay, so I know there is some online search things that people can download onto their computers.
There are. I mean, so LIGO has this glitch identification system, doesn't it? Do you know much about that?
Yeah, I haven't used that. So, this is not something that I've ever participated in. But yeah, there are sort of crowdsourced or computer
citizen science
kind of things. But being part of gravitational wave detectors
Einstein
in
at
the
home,
future,
I think, is the big one, where basically we get to use your computer a little in the background to try filter all the data.
Yeah. And the glitch detection is when you have just a random event in the LIGO data stream, I think, and there was actually one happened in the middle of this neutron star merger. And you see the big glitch, and I think these are happening kind of all the time, right, in LIGO, and so there's thousands of images of these things, and there's sort of too many for the LIGO team to go through and look at, and they can
so
you can go through and look at glitches.
It's a huge thing when people actually do this, because I mean, like we said, there's only so much money that goes to us, and computational power is a huge expense. Like running all those simulations, like to actually see what a waveform is. I mean, the man hours that go into actually just developing the code, but then actually the computers to run the code, like it's costs quite a lot of money. So when people like all over the world just let us have a little bit of their RAM or their computer power, it makes a huge difference to the collaboration. So everyone is actually really, really happy the success of these projects like Einstein at Home.
I guess the other, I mean, if you want to be
if you
part
want to
of,
really be involved,
yeah, then you go to university and you study physics or engineering, or we have a wide range of
do science.
Science and technology.
Because you can really do anything. Like if you really like gravitational waves, I mean, and you really want to get into the field scientifically. I mean, there's, as you can see, we all have different backgrounds. So I mean, if you go to college going, I kind of like science, but then like I went in going, I really like physics. I don't want an office job. I want to work in a lab. And then I went into physics and I was like, I don't like labs. I don't like them at all. I keep destroying stuff. I'm going to be over here with my equations. So I had it completely wrong, what I thought I was going to be good at. But it turned out, all the math stuff I was doing was very applicable to this kind of stuff. So, go find what you really like. It could be in the lab, it could be in the thing, and, find out what you're good at. And then, then like a project like this, they can use you no matter. So many skills. Like, you have optics, condensed matter, then general relativity, astrophysics, data analysis. There's just across the board. So I just say, go into science, see what you like, see what you're good at, and then you can find a route into gravitational waves astronomy. Okay, and I think we're going to wrap it up now. So we are going to actually stay online we're going to shut the video. I think everyone's seen enough of us now. But we are going to keep answering questions on the feed. So if you still have questions and you don't feel like you got any answers or the answers particularly you wanted, please keep sending them coming. We're going to keep addressing them. This was all brought to you by the University of Florida. Thank you for reminding me, guys. The physics department there, and we're in the Dark Cosmos group. And so I'd like to thank all the panel for joining me and taking the time out. Also, there's a crew of people behind me here who've been working chaotically, furiously going through the feeds. So I'd like to thank all of them. Oh, there they are. So I have undergrads, postgrads, postdocs. No professors checked on us to make sure we haven't burnt the place down. So they obviously had a lot of faith in the kids. But yeah, thank you so much for joining us. We hope you enjoyed this look into gravitational wave astronomy, and hopefully we'll see you again sometime. Thank you. Are we offline?